This week we're going to start creating the actual 3D geometry using a variety of techniques in Houdini. We're going to be utilizing heavily the Voronoi SOP as well as the point VOP to create interesting geometry that we then convert into volumes and do further processing on it. So I'm going to go over a variety of examples. We're going to start with some easy examples and then slowly start increasing the complexity of the method to achieve some more complex details. And we have tons of assets to go through in a variety of examples that hopefully each one of them will teach you guys a way to achieve certain details in the geometry, and hopefully you guys will be able to create some very interesting stuff. And thanks everyone for watching this, and let's get started. Bye. The first thing I want to start with is explaining what we're going to be doing inside of Houdini. And the first thing that we need to fully understand is what is a volume and what's happening with the data when it becomes voxels. So I'm trying to draw my domain here, and this is the domain where the data is going to live. And when we have points, they're just living in space XYZ coordinate. When we have volumes, we're restricted to a specific domain, and that domain has data filled in. So let's say voxels, and these voxels have value. In order to process either the value or the information of the voxel itself, if we need to change the value of an existing voxel to, let's say, multiply the density, we need to use a volume VOP. If we need to change the voxel information to get its data from somewhere else, let's say we want to move these guys, we need to use a volume VOP with a volume sample node. And the main difference between having a volume and a surface is this. When we have a surface, let's say a circle and another circle, and we push them, we expand each one of them, so they start intersecting. That intersection, that overlap will create some problems in the geometry when it's a grid or something. It will overlap. And if this geometry is connected, let's say you have two faces, each one looking at facing this way, facing the other. If we start pushing the polygons, let's say these are two rectangles, if we start pushing the polygons, we're going to create a geometry intersection, and that is a big problem. Once we start using volumes, let's say we have two rectangles that are volume based, and we start pushing the data in this direction and in this direction, they will blend in. They will create a nice blend in, so we won't have any issues. And let's take a look at, first of all, taking a 3D geometry and converting it. And then we're going to process some of that. We're going to try to manipulate some of the voxels in Houdini. Now, we talked about this a little bit in week 3 when we did the height field, but in that context, it was purely 2D volumes. So in this case, I want to go over the explanation again and make sure that everyone understands the idea. The other thing that I didn't explain is converting existing geometry into volume. Now, Houdini has two types of volumes. There is VDB volume and the Houdini native volume. The main difference is VDB is much more efficient, much more optimized. We can push the quality a lot more, and the memory will still be reasonable. With the Houdini native format, the data is going to be much heavier and much slower. And so we're going to be using VDB, which is what Side Effects encourages everyone to use. And let's start by creating a sphere. Okay, I'm gonna create if we hit tab and we go under, I believe, VDB or volumes. Yeah, there is a tab called VDB, and it contains everything related. Let me go up a bit more. It contains everything related to VDB and creating it, manipulating it, and everything. And then once we have the data, it's just voxels. So processing the VDB voxels, the VDB volumes and or Houdini native volume is done through the same process. So there is no difference when it comes to that. And we can take any geometry and convert it into a VDB using the VDB convert, VDB from polygon. And there is if once you start typing VDB from, there is a variety of ways to convert existing data in Houdini into VDB volumes, and this one is for fluids. Same with this one is for particles as well, and this is the one we need. It is always recommended to have, well, it is required to have a closed surface, okay? Otherwise, the VDB from Polygon won't be able to generate proper volume for that data, and we'll try to treat it as a surface. Actually, let me create a grid and connect that. You see, it's trying to do something, created a box, but it's not. It can run into issues when you have a complex geometry with holes in it. So we have to make sure that that's not the case. And once you create this this node here, it is set by default to distance VDB. We're not going to be using this at the moment. We're going to do that at the next phase, once we understand how to use the fog volume. And we have to uncheck this and then click this fog VDB. And now we have a density field. Okay, we have one field. It is called density, and this is the resolution. We can lower the resolution. We can increase the resolution by lowering the voxel size, which means that we're gonna have more subdivisions. And let me change this to polygons and increase this to 20 so we get nicer edges. And then you can see there is this option here, fill interior. Right now it's trying to optimize so it only places data where it thinks it's needed to save, to make it more efficient. We need to fill in the interior, and later we'll understand what's the advantage of that. But basically the volume is filled in with data all the way until the center of it, so everything has data. I have a little bit of display issue since I upgraded my graphic card, and I think this is since I upgraded the driver, you can see there is a little bit of flickering, but it shouldn't be an issue. We're not going to be looking at the volume too much, to be honest. We're going to be looking at it as a surface. So once we have this, we're now dealing with volumes. We can use all the VDB tools to process this or do any operation on the volume, and we can use the volume VOP as well. Now let's put down a volume VOP, and let's try to take the density and change it a little bit. So let's create a noise. Okay, we're going to generate a 1D noise because it's a float field, it's not a vector field. And we're going to multiply the density with this guy. And it killed it because the noise pattern is too big and we're not seeing it. Basically it multiplied everything by 0. Let's try and increase this. Yeah, it's still too big. Let me make sure the sphere is big enough. Let's increase it to 100, and we have to make sure to fix this because it's based on the unit scale. So if I left that value, it will generate a volume super dense. And I have the shortcut to turn on and off the manual, and I always use that because this node, if I clicked on it, it will freeze Houdini. So let's set it to 1. Okay, we have some data. Yeah, and now we're seeing that, you can see that we're changing the volume. Now look at how the data is, there is data inside the volume. Now let me go up and create a light. And I'm going to create a very simple light rig with 2 distant light. So one is pointing this way, and let's make another one. Sorry. And let's make it point the other way. And let's hide this so it's faster. And let's change the colors a little bit. Okay, cool. Let's take a look at the volume. Cool, so now we have our volume. Let's go back and try to play with the noise a little bit. I don't want to change it so that it removes data from here. Let's set it to 10. Yeah, so the reason this is getting subtracted is because this noise is returning a -1 to 1 range, and I'm going to simply clamp that and say the minimum value for this noise is going to be 0.1. We're going to see it still 0, so let's set it 0.1 to be the minimum, and now we have data overall. Let's reduce it more. Let's go even further, 0.1. Yeah, see it here. Let's go 0.05. Cool, so now we have an interesting volume. Now, obviously we cannot do that with a sphere geometry, but let's take this data here and convert it back into a volume, into a mesh. And the way to do that is using a VDB convert node. And this can take any VDB volume and convert it into a variety of other formats. So for example, we can take a VDB volume and convert it into a Houdini volume. And if I middle click, you can see it says volume now. And if I middle click here, it says VDBs. So this is a Houdini volume. And then we can change, we can set this to polygons. And now everything disappeared. Now the reason for that is because this ISO value here is set to 0. We need to move it a little bit to capture the information we have. Now the ISO surface represents the data at the edge or the extremes of this volume. Okay, and if we set it to 0, it's basically not capturing anything. You can see already here. Let me look at that. Let me template this. You can see that the surface is inside. The surface generated is inside because this ISO value is representing not exactly the edge value, but somewhere deep inside the volume. So we need to play with this until we get the sphere to match the, sorry, I need to, yeah, something like that. Let's try 0.1. Okay, that's close. So now we've converted the data back into a mesh, and see how it is all quad based, which is really cool. So that's the volume converted into a mesh. You can see here we have P and a name attribute. And if we take this and convert it into a mesh as well, we should be able to get something really, really interesting. And look at that. We now have, this is this is where the data is set to 0.001 value for the minimum, and then everything else. And this was just one noise. Now, there is one interesting behavior with this that we don't get with any processing, with any other operations. Now, actually, you know what? Let me turn off the min. I want to show you guys something. Cool. So let's go back up. Now, see how the data is changing as it gets deeper into the volume. And this is very interesting because what it means is we can push volume, we can push actual specific details from a volume, and this is very, very powerful when it comes to creating rocks formation. You see this hole, for example, here. There is no way you're going to be able to sculpt that or create that except with volume. Now let me increase the resolution a bit, so it's 200 now. The final poly count is 280,000. Let's increase this to 0.3. Obviously, it's gonna take longer to generate first the VDB volume for the mesh, and then it's gonna take a bit longer to convert it as well. Some of the heaviest rock I had took about 10 to 12 minutes to cook the entire graph, but it's super high res. For example, this one here, I think it was about 8 minutes, but you can see the resolution already that we have here. Yeah, so this is the kind of details we're going to be able to get. And I think it's totally reasonable to wait 8 minutes to generate this kind of mesh. Cool, so it's done. And let's see the point count, 3.3 million. Actually, if you think about it, this is really, really fast, especially with how much voxels we have. You can see how powerful this technique is. Now, this is just an explanation, and then I'm going to show more benefits of using this method and hopefully start creating some actual geometry. So now we're going to look further at how we can manipulate the volume data. And so far we used the volume vault to manipulate the density, and if we look at the edges of the sphere, we can clearly see that. We can easily see them. And all what we've been doing so far is changing an existing value of the voxels, and because all the data outside has a negative value, has a value of 0, nothing happened to there, nothing showed up. And so in order for us to actually tell this voxel to go look up its value from a different location, we need to use something else. We need to use the volume sample node. So I'm going to create a volume vault, and if we dive inside, let me lower the resolution a bit so it's faster to work with. And let's create a volume sample node. I'm going to connect the sample position. The file is the first input, and the primitive number is 0, and this refers to the field order, so 0, 1, 2, 3, and or we can use the name if we want that. So we can specify density here, and let's connect that. We should see no difference because we're not changing anything. Now if we create a noise and connect the position and add this noise to the current position to modify it, basically to disturb that a little bit, we should see some difference. We should see something happening. So let me reduce these guys, and let's increase this value. Cool. So you can see already that we're getting changes in the silhouette, and the reason for that is because we're offsetting where these voxels are sampling their value. So this point will sample from here, this point will sample from here, this point will sample from an empty area, so we get black in that area. So let's increase this to 100. Cool, let's go even higher. Let's try 500. Cool. Now the thing that I'm noticing is as we increase the value, we're still not getting any data outside. Well, why is that? Well, the reason for that is because VDB is trying to be very efficient, and there is actual pruning happening for the voxels that didn't have data before. So if when we try to add values to them, VDB still keeps ignoring them. And what we need to do is we need to expand this domain here, because we're also hitting the edges, and so these guys will not find data where they can sample from. So we need to expand the domain. Now how do we do that? Well, we can use a VDB activate node. The name doesn't mean too much, but there is this feature here called expand, and you can see already it expanded it by 1 voxel. Let's add 10. Let's add 25. Let's go even higher, 50. And the higher we go, the bigger the volume is going to be. Now look at how the data is. We don't have that sphere anymore. It's completely gone. And I just realized that the noise I have right now is a 1D noise, so we need to change that to 3D. And boom, we don't have that sphere anymore. Obviously there is a little bit because that's the original data, but if we start playing with these, yeah, exactly, we don't have the sphere anymore. It's completely broken. And let's set this back to 1. Cool, so that's our sphere, and let's try increasing it. So 14. Yeah, you can see how the silhouette is is changing. Now this is very, very powerful, because what that means is we can take a volume and push data out. Now let's take this VDB convert node and connect it to this guy and take a look at the mesh. Boom. Now we have something very, very interesting. Now we are not making something that is not feasible with a mesh. Okay, but let's try to do something very a bit more complex. Or actually, let's try and push the noise. Cool. Let's go back to 100. Nice. Now this is the stuff I'm talking about. With volume, we can push data outside. So look at how this curving out, and it is generating the data outside the domain, and it's creating very, very nice, very interesting curvature. Look at this. This stuff, there is no way we're going to be able to create this with a mesh, the way the volume is pushed. Now why is that? Well, let me create another noise pattern. Let's create a whirly noise, the one we like, and let's subtract F2 minus F1. And let's connect this to add the values to the sphere. Now the size looks really small, so let's reduce that. Let's make it bigger. I'm gonna turn off the cooking mode. Let's set this to 0.1, and let's see what we get. Okay, we're not seeing any results, so let's increase the whirly value by multiplying it. Cool, now look at that. And this is the stuff I'm talking about. See how this volume is getting pushed out, and especially this guy here. See how it's coming out and have a very interesting curvature. Now the reason for that, I'm going to explain the reason for that. Why? Let's try and see that guy. See how it's being basically born, and it's going to expand as we push the data. And this is very, very powerful, because we can push actual 3D object, actual 3D rocks from the mesh, and not just have a 2D displacement that changes the value. We can do something much more complex than that. And same goes here. Now the reason for this looking this way is because we're just pushing everything along one axis. This is a 1D noise, and we need to look at another way of pushing the data, which we're going to talk about. Maybe, yeah, we'll talk about the next method in a couple of videos. Right now, I want to start creating some geometry, and I want to show you guys how to make use of this to create some interesting details. Now, obviously, this part here. Let me do one quick thing. I'm gonna connect this. I'm gonna add a little bit of noise, and this idea is at the base of everything I've been doing. So instead of passing P as it is, I'm going to add a little bit of noise to it and connect that. And let's change the value to 10 and take a look at the result. Let's increase it to 100. Cool. So now we can obviously take a look at the volume using lights, but it's hard to tell what's happening. The best way to visualize it is by converting it to a mesh. Now see, once we added that noise to the, let me turn it off. And let me make a copy of all of this and turn it back to 100. Cool. Now see how this is the original result, and once we started disturbing P, we're getting something really, really interesting. And this stuff it just works. Like, you take a sphere or a box and you add this, and it starts to look like rocks basically. And there's not so much into it. I mean, we're getting a lot of details already with using this method. Now let me show one more detail. Like this, I want to save the file. I want to increase this and show you guys quickly what kind of resolution we can get. Cool. So let's see. So see how interesting the data is here. We're just pushing volume in, and these kind of details are really interesting. And this is at the core of everything I've been doing with the volumes. Now there is a lot of interesting stuff that we need to do for us to get interesting details, but this is like the main core. Now we're doing a very primitive volume displacement, and we're going to learn more advanced technique in a couple of videos. Now the last thing I want to show is very interesting behavior with volumes. Let me increase this to 10, and I want to make a box. Okay, and let me transform this box and push it up a little bit, something like that. I'm going to merge these guys. Okay, cool. Now see the kind of details we have here. Let me copy, which one? Let's copy this. I want some displacement, so let's copy this guy. Actually, let's copy the whole graph. And let's take a look. Okay, cool. Interesting. We're not getting any data. Okay, cool. So we have the volume there. Let's take a look. Maybe increase the resolution a bit more. We need just a little bit of voxels. We're not gonna change that drastically. I accidentally hit 200, and see now it's the Houdini is freezing. So you have to be very careful, because it can lock up the machine, your machine, even if you have a lot of memory. Okay, set this to 20, and let's take a look at the volume. Now it's being displaced too much. Let's tweak a couple of values here, and this guy here, and let's increase this to 0.25. Okay, now let's convert this. Cool. Now the main thing, actually let me turn this off. The main feature I wanted to show is this is the original result. This is the original boxes, and you know what, let me do it without any noise. So, and then we converted that into a volume. We take that volume and convert it back into a mesh, and look at the seams, look at the edges that we're getting, how it's blending between the two different meshes and creating that result. Let's play with the ISO value. And you can see we can push inside the volume and tell it basically which level this volume knows how far it is in as it goes deeper, and there is an ISO values, and the closer it gets to the surface, the lower the ISO surface. So 0 means it's at the boundaries of this, and basically there is no data for it to convert, so we have to set it to at least 0.01, which starts picking up some details. And as we increase this value, it's going to push inside, and you can see what kind of details we're getting. Now the main feature I wanted to show you guys is Let me increase this a bit more. The main feature is blending between the two volumes. And let's increase this, let's lower this 0.01, and look at that. This is the detail I was looking for. Let's increase this 0.1, set this 0, and basically we can blend nicely these two meshes together instead of having any sharp transition. Now let me rotate this a bit more, something like that. Now look at how sharp this is. Once we convert it into a volume and then back into a mesh, we can create very nice edges between the various geometry, the various pieces. And this is very powerful because we can have any complex geometry overlaid on top of each other and then create nice blend of the edges between the various pieces. And this is very important to make something look realistic and to make it feel like it's all one material put together. And in the next video we're going to start looking at how to create something interesting with the Voronoi and use the volumes to process it. So now we're going to start creating some more interesting geometry to start with and then use the volume to add extra details. And what I'd like to do in this case is start with a grid and add some Voronoi fracture to it and create something interesting to basically represent a ground with a lot of small pieces overlapped on top of each other, or big chunks of rocks overlapped on top of each other. Now I'm going to use the Voronoi fracture, and hopefully all of you guys are familiar with this. I'm going to connect the Voronoi node and then scatter some points on this grid, and let's set it to 100 and connect this. And there is a feature that I like a lot, which is the visualize pieces. Now we can see the size of the parts here. You can see they're very uniform except here. So I'm gonna uncheck relax iteration, and this creates a little bit more randomized points, and I'm liking this already, but I want to add a little bit more variation to that. So I'm going to create a point VOP and simply add noise to this. So noise, add the noise result to P and connect P, and let's expose these guys. And now if we look at P, we're shifting everything along the all direction. Let me change this to 3D, and I want to flatten that, so I'm going to put transform. I'm going to scale everything along the x-axis. Okay, so everything is flat. Let's take a look now. And we should have more randomization of the points. Cool. So let's leave it at that, and we can also play with the frequency. I think 1 is fine. Yeah, it's fine. And I want to add one more thing. I want to add point replicate node, and this basically takes an input, a set of points, and duplicate points around them in a using a very specific shape. In this case, I want to use sphere, and I want to set the point count to 3. And I'm doing this before the transform, so everything gets flattened. And you can see now we have more interesting breakups. We have small and big and a variety of chunk sizes. And anytime you have fracturing with Voronoi, it is very important to pass in the lowest geometry we can, even though we need some details in here. And that's what I've done. I've passed in a very basically one primitive, one polygon, and I'm fracturing that. And if I wanted to add division, I'm going to use a divide node, and this way it's much faster than Voronoing a high-res geometry like this and then using it. So we Voronoi it first, fracture it, and then we subdivide it. Let me copy this in case we need to change those values. Paste relative reference, and let's increase a little bit of points. Sorry, 0.005. So much. 0.05. Okay, cool. So now we have this, and let's hide the normals. And I'd like to add a little bit of randomization to this. So the two axes that we're interested in disturbing these points along are the Z and Y, and we just need to leave the X as it is. So I'm going to put down a point vault and create a vector to float, and then an add node, a noise node, and as always add noise to P, and we're going to basically change the X and the Z and Y axis. So I'm going to copy this again, connect it to the original position, and then from those two float to vector, and we need these two guys and the original X. And let's connect this. Okay, let's make sure we're looking at this node, and voila. Now let's change this to 3D. Cool. And now we have some very interesting pieces and fracturing happening. Now there is a little bit of overlap, you can see that. And this is one of the main limitations with geometry. But what I like about this is the fact that we have very nice and organic edges, and they're all blending together. Let's reduce this, something like that. I don't want to get a lot of overlapping edges because that may cause some problems. Okay, cool. So we have this, and let's add something else. Right now everything is connected together. There is no cracks, there is no seams. And what I like to do is I want to add a little bit more noise to add a little bit of cracks in these guys. So what I'm going to do is I'm going to first create a connectivity node, and with this node it's going to create a unique value called class per block. Okay, actually let's turn off the visualize pieces. And let's create a color node and create a random value based on that class attribute, just to show you guys. Cool. So now we have a unique integer per block, per group of per piece, and this is great because we can use that. So let me put back the color. I want to use that, and let's put down another point vault. And this time, instead of generating the noise using P, I want to import that class. So bind, let's import the class attribute, and let's generate a noise based on that. Now I'm gonna connect a noise flow this time, and I'm going to use the P, make sure I'm going to use that value in the noise. Now let's connect this to color. Let's make sure we're getting the correct value here. Let's try a random. Okay, let's go with the random value instead. You can see now we have a unique value per piece. And what I'm going to do is I'm going to add a little bit of noise. Actually, let's copy this noise here, and let's paste that. I'm going to copy these two guys and reuse the same noise. Okay, but now what I want to do is I want to add this to be an offset, so each piece get a unique value. Now right now we're adding the same noise, same frequency, and I'm going to lower the frequency and lower the amplitude as well. You can see we're getting some interesting cracks happening. Now we're getting the same distortion along the same offset along the X and Y, and I want to change that. So what I'm going to do is I'm going to add a constant, and let's say 500, generate a new random value, and do the same thing. I want to create 3 vectors. Okay, float to vector node, and this is going to be my offset. Cool. So you can see now we have very interesting cracks. Obviously there is a little bit of overlapping, but I don't think it's a problem. And what I like the most about this is having gaps, and then it closes, and then another gap. And that's very, very realistic and interesting behavior to get in this, for example, here. Cool, so let's continue with that. And I'm going to transform this. I want it to be flat. There is only one reason I started with this, because I've really set it up. I want the values to be similar, and there is no reason for you guys. You should start with the grid aligned in that way. Now, one thing I like to do is I like to add a little bit of thickness to these guys. So I'm going to extrude them. Poly extrude. Let's add, that's probably too much, 0.01. It's maybe too much. Okay, let's set this to 0. And let's use the local transform. Okay. Okay, cool. Now we have a little bit of depth. They're not just flat. And the last thing I want to add is a little bit of variation in terms of size. And one more thing, let's take on output back. One more thing I like to do is I want to make the bottom flat. I want to make these guys, the ground parts, bigger. So what I'm going to do is, let me think. Actually, let's do that afterward, and I'll explain why. Now, what the effect I want to do is I want to add rotation to these guys. So we have this rotating this way, this rotating this way, but I don't want random rotation. I want each piece to rotate based on its centroid. And the easiest way to compute the centroid is using this method. So the first thing I'm going to do is create a name attribute. And these nodes are used for preparing data for destruction, but we're going to use them for a completely different purpose in this case. So all I need from this node is to create the name attribute. And if I middle click, you can see we have name attribute. Now each piece has a name attribute. Cool. The next thing is I want to pack these guys. And what a packed primitive is in Houdini is basically you get the OpenGL display of the geometry, but in reality it's just a point. There's only one point. And that point is at the centroid of the piece. So if we put down another assemble, let's call this create name adder, and let's call this create centroid. Now in here I don't want don't the name attribute because we have that. I want create pack geometry. And you can see the display says displayed as full. I don't want it as a full geometry. I want it as centroid. And now if I template this guy, you can see each point is at the centroid. Now all we have to do is copy that point information, copy that position back into the mesh. Okay, now let's store these positions, these points. Let's store their position into a rest attribute. So I'm going to connect a rest. Now P is copied into a rest attribute. Let me prove that. So this is P, it's the name attribute, and this is the rest. Now we need to pass this rest back into the original mesh. So each piece know about the rest, each point know about the rest. Let's do that using an attribute copy. Copy. Cool. This is the target, this is the source, and I want to copy, what do I want? I want to copy the rest. And I want to match by, this is why I created the name, I want to match the pieces by name. So match by attribute name, but this node is going to complain. The reason for that is because the name attribute here is a primitive type. So we need to promote that to be point to match these guys, because here it's a point attribute. So I'm going to put down an attribute promote, set name from primitive to point, and I want to change this to first match. It shouldn't matter, but I want to do that for safety reason. Now there's no more complaining here, it's all good. And now we have the position copied. Let's put down the point VOP and prove that. So let's dive inside, import that rest attribute, and let's mix the current position, this is basically a blend shape, with the rest. Okay, so see, that's the original position, and this is the centroid position. Now each point has the centroid set. This is perfect, because what I can do is I can use a transform matrix. I'm going to copy that, and the pivot is going to be this. And now I can rotate these guys, and boom, they're rotating based on the centroid. Cool. So let's do this. Let's take that the rest attribute, because it's one value, it's the same value across all points, and generate a noise. Okay, let's do a noise. Yeah, let's do a noise. This noise goes from -1 to 1, so let's fit that. And let's generate 3 noises, so X, Y, and Z, and I want to fit that between -1 and something. Let's create another one, and let's create another one. And now we need to connect that into a float to vector. We need to create a vector from these guys, and that's going to be our rotation value. And now we can use this. Let's say the min, I want the min of the X to be -5 and 5. This to be, let's say, 15 to -15, which is probably too much. And let's say this -10 to 10. And now we have, see that variation, which is very cool. So let's add more to this. And obviously, if we didn't like the pattern, we can always change this. You know, we can always vary this, and we can get some very, very interesting results. Increase this. Okay, cool. And now we have something very, very cool, I think. Now we're ready. Let's start doing some volume processing. So let's continue working on this, and the next thing I wanted to do is I want to add a little bit of noise to the overall geometry. I don't like how everything is flat, and we can easily do that now using a point VOP. Obviously you guys know this, and I'm going to create a noise attribute and add that to be just to disturb things a little bit. I don't like how everything is uniform. And let's expose these guys. And lower this. And let's compute the normals so we get proper shading on this. Let's facet. Normals, okay. And let's lower this. Increase the frequency. Something like that. I think it's too much. Just a little bit. Okay, cool. Now that we have that, I wanted to transition to volume. And if we have any intersection, if we have any overlap or anything like that, everything will work just fine with volume. So I'm going to put down a VDB from volume and set this to 2 just in case it goes crazy. And I'm going to turn off distance VDB and generate a fog. And let's lower this until we start seeing the details. So make sure that this is filled. Okay, cool. Now we have our details. Let's increase this even more. 0.03. Cool. Let's increase it a bit more. Okay, cool. Now you see we don't have, it's not displaying the density, well, it's displaying it correctly, but it's hard for us to see. And we can use a visualize node to process the density of the volume just in the viewport. This won't change the actual value of the density, but it's going to change it in the viewport. So I can increase the density to 10 and turn on the lighting. You can see we have the volume of our mesh. Now all I'm going to do is convert this VDB back, VDB convert. I want to convert it back into a mesh. Just take it into a volume, convert it back into a mesh. Cool. Now we're not getting anything because of that ISO surface, so we need to set this to something. Let's try 0.1. Cool. And this is basically what I was talking about the whole time. See these nice blend in transition in the mesh? That's what you get with volume. Cool. So let's increase. It's very high res, so let's increase this to 0.05. Let's increase this a bit more, 0.1. I want to capture more details. Okay, cool. Now you can see now, the more voxels, the slower it's going to be. We can see we're getting a lot of details. Now it's getting this tapping effect, and the reason for that is because we're reaching the limit of the data. That's how far, that's how much data we have. So we need to be a little bit careful with that. But so far, all the tests I've done, that stepping effect with rocks actually really helps. Now this is what I've been trying to get to, is this nice blend in. See these guys? That's really cool. We get very, very interesting cracks. We get these kind of details. We get this, and we didn't do any processing yet. We haven't started yet. So what I'm going to do is I'm going to take this mesh and I want to add something to the bottom of it. So I'm going to transform it and copy it. So I'm going to transform this 180 degree, and I'm going to merge it back and transform it down. Okay, cool. Something like that. Let's take a look at the result from the top, and I want to get that. I wanted to cause some issues with the mesh, and I will show you guys why. I wanted to create these effects and see what happens. And we can convert this into a volume, obviously. Let's do that. Cool, and let's convert this back into a mesh. Cool. So see, we're getting a lot of interesting details now. And even those overlapping issues, they're actually creating some very interesting details here. It's not, I really like all the extra bits that we're getting from that operation that we did. Now, the only thing I don't like is the fact that we have stuff at the bottom, and I want to fix that. Now, the great thing with volumes is that we can do very complex Boolean operation on them, and it's going to be very fast and very efficient, and the result is super clean. So we need to basically clip this data, and the easiest way I found is to actually create another volume and then subtract that. So I'm going to put down a bound node, and I'm going to template this, and with this bound I want to move it down. Sorry, I want to do that, and this is basically how far I want it to clip. Let's go up a little bit more, something like that, and let's expand the boundaries. So 0.2, 0.2, 0.2. Cool. So we have a little bit of room, and I'm gonna copy this, paste it, and now we have a flat polygon converted into a volume. Sorry, a box converted into a volume, and it's pretty high res. So I'm gonna link these two guys together and lower the resolution for now. So let's set this to 5, and let's do the Boolean between the volume. Now VDB has its own set, and it's called for doing volumes, and it's called VDB combine. I'm going to connect the first one, the second one. And the operation, it says copy A right now, and I'm going to change it to subtract, and that basically subtract all the data inside from this, subtract the two, basically A minus B. Now if we convert that, we should get something Still very interesting as well. Now it's probably too much clipping that we're doing, and the resolution is also very low res, so let's increase that first and see if we get the proper data that we need. Okay, cool. It's too much, so let's do one more thing. Let's lower this a bit more. Sorry. Something like that, and let's take a look at the result. Okay, cool. And now we have the ground hopefully clipped. Not so much. Let's see what's happening. It is clipped. Nowadays, yeah, it is a subtract operation and it's working. It's just that it's revealing stuff from the interior, and unfortunately there's not so much that we can do about that. So we're gonna leave it at that for now and focus on adding some details. Now, once we are in volumes, we can obviously process this. And what I'm going to do is, this is the volume, and I want to create a volume VOP and add simply noise to that. So I'm gonna create a volume VOP node, and I don't want to change the density, I want to change the detail. So I'm gonna create a volume sample and add node. First input, primitive name, that's fine. And then noise. Let's connect this. Okay, cool. And then let's change this to 3D. And let's expose these guys. And let's go up. And look at that, we're distorting the volume. It's too much though, so let's convert it and take a look at what we have. It may result in some very interesting stuff as well. Cool, so that's the result we have, and let's increase the frequency. I want to get finer details with this. And right now it's changing the volume as well as converting it. And that's a lot of processing, so it's doing a very heavy operation, and it's still, I think it's reasonably fast if we think about all the stuff that's happening. So it's 7.4 million points being created every time, and I need to change this to 10 and lower the amplitude to 0.1. And again, I'm turning this on and off constantly. So if you guys see me change values but not getting anything, that means I'm changing it's off. So let's reduce this even further. Okay, cool. And now we're getting some very interesting details. I'm gonna copy this one more time, and I want to increase the details to 0.5, 0.5, 0.5. and the amplitude to 0.1, and let's see what we get. Cool, so it's a much bigger noise. And the other thing that we can add is, instead of changing the z-axis, I'm not going to do that. I want to remove any without changing the y-axis. So I'm going to copy this one more time, paste it here. And instead of changing the 3-axis, I'm gonna create a vector to float. Vector to float from here. Float to vector. And I don't want to change the y-axis, just these two guys, the x and z. And let's take a look at that. And we should see the more breakups here. Increase this. And remember, we're dealing with 3 million points at the moment. So let's do one more thing. Let's increase this a bit more, because we're just pushing on the X and Z. I'm not too worried about the data itself. I'm actually going to lower this to 2.01 because I don't want to change the height too much. I want to leave it as is. And this is, you can see already, that's the stuff where we can get with volumes. And this is, yeah, there is no way we can get that with meshes. See how nice curvature, how the curvature we're getting is. A lot of cool stuff. Okay, so that's our first geometry. And sorry, I'm going to completely turn this off. I want to get flat polygons in few areas, and this detail here is breaking that up. Still, which one? So let me turn off this as well. I'm trying to remove the stepping. It could be from the Voronoi noise itself. It could be from the convert that it's not picking up the right levels. So let's try 0.05 here. But this is really cool. I'm liking the details a lot. Turned out to be much better than the first version I did. And I think the reason why we're getting all this stuff is because of that noise that I added at the end. Which one is it? This one. So that's cool. And let's add this before. And let me limit this as well. So vector to float. This vector to float this. And I don't want to change the height, so float to vector. These two guys. Okay, cool. So let's try this one more time. I want to get flat polygons on the surface. I want it to be smooth surfaces, but only get details at the edges. So this is the stuff I'm looking for. And see, now we're getting perfect blend between the pieces of the rocks here. A lot of interesting build-ups between the parts, a lot of interesting cavities and very sharp details. And obviously we are just starting, so this is definitely a very good start. And you can see already there's a lot of details here, and we're not doing any displacement or anything like that. Now let me do something a little bit crazy, and let's see. So this is really high res. You can see it's 14 million voxels. And I'm gonna lower this even further. And I want you guys to see. Now, obviously, I have a very decent machine, but this processing in Houdini, the SOPs, is not all multi-threaded. So having a 6-core CPU with higher frequency may be much faster than having dual Xeon with a lot of cores on them. And I don't think you guys will have any huge difference in terms of computing. And even if it takes, yeah, it's done already. Even if it takes, let's say, 5 minutes to generate how much? It's done as just displaying the mesh. 9 million points it took. Let's see, 2.99, so almost 3 seconds, which is insane for that node. And you can see all the crazy details that we're getting using this. And the cracks, where is the cracks? So I'm looking for an example. Yeah, this is the kind of, see here how it starts and then fades out and then starts again. We can add all kinds of details to this. And I think I'm gonna stop here. Hopefully you guys like this, and let's continue with doing some more stuff. So now we're going to learn how to create more rocks formation, and we're going to create a standing rock that has a very unique look to it. And and by showing all these examples, hopefully by the end you guys will have a very good idea of how to achieve certain things. Now there is a little bit of duplication in terms of process and how I achieved certain things, but hopefully you guys will find that useful, as well as I have to do that process to show you how I created these assets. Again, the level of complexity is going to grow as we continue and progress throughout the examples. Now I have the shell, it disappeared. I want to create an asset because this one we made on the fly, but I will save as a proper asset. So I'm gonna create asset AAC workshop, and I want to create a artistic standing cliff. Should have added R&D. Yeah, let's add an R&D. Cool. So let's start with this. Okay, cool. And our geometry here. Cool. And I'd like to start with a tube. This is my starting geometry. And I'm going to copy it and paste it from a previous scene so that the values are reasonably the same. And I'm going to start by creating a VDB from volume, and I will explain why is that. So with this VDB we can set it to density, and when we have volumes we can scatter points a bit in a more interesting way. So we can fill this tube here with points, and this can create some very interesting results for the Voronoi fracturing rather than just placing them on the surface. So I'm gonna leave the points at 1000, and I'm gonna create a Voronoi fracture and just fracture it. And I'm gonna show you guys a variety of methods on how we can create a base interesting geometry that we then process with volumes. And I'm gonna be combining Voronoi, point VOBs, a variety of techniques that will then be used in a mixture with volume. So it's not just volume stuff that we're going to be doing. And now we have that geometry subdivided, and I'm going to assemble this, and by assembling it we're converting it into a packed primitive. And what does that mean? It means that each piece is now can be selected, and basically each block is like a group of points together. And this is very interesting because we can easily select parts and delete them, and we have a very interesting geometry in there. And if we create a delete node and delete the outer details, so I'm going to create a delete node and set it to bounding box, and we want to delete the points because once we convert them into packed primitives they are just points. So we have 956 points, and that's what the delete node wants to work with. You can see now we have a bounding box set to in this area to delete those guys. You can see now we're deleting whole chunks, and this is very useful because we don't leave geometry with just faces or things like that. So I'm going to change this to a sphere, and I'm going to make it bigger to encompass the whole volume, and let's increase it. And instead of deleting selected, I want to change it to delete unselected, and let's scale it down. Scale it up, and let's reduce this to 1 and this to 1. Cool. Now look at the details we're getting. We're deleting everything, and we have some very cool silhouette for this, but it's very uniform. Okay, so and the last thing I wanted to do is I want to delete the top and bottom because it's creating these weird shapes. So I'm going to put down a delete node and set it to bound again and move it up, and make sure we set it to points because that's what we want, and delete only the points that we don't care about. Okay, cool. And let's do one more copy of this and move it down to clean up the bottom as well. Okay, cool. And let me check one quick thing. Cool, so now this geometry here is a little bit uniform, and what I like to do, I'm gonna copy this again and move it up and delete everything except a block of pieces, basically. So delete non-selected, I want just that. And what I'm going to do is I'm going to transform this. I'm going to stretch these guys, and you will see what kind of result we're gonna get. Set this to 3, and this is the stuff, this is the result I'm looking for. Now you can see we have very cool organic shapes going, and we have some very cool shapes at the top as well. And this is very you can use this as an in-game asset. Maybe once I finish working on it, you guys will have a good idea. It has a very unique style, and it's really hard to create this kind of organic shapes if we're not looking for something photorealistic. So let me start working with volumes now. I'm happy with the original geometry. Let's create VDB from polygons as always, and let's make sure the voxels is set to a reasonable number. Change this to density 0.1. Let's see how much we get. Let's increase it to 0.01. Cool, so now we have a reasonable amount of voxels, and we can start processing it. We can start adding details to this. Okay, so let's create a volume vault, and by now we're going to be doing this a lot. And honestly, I don't want to make OTLs. I'm fine creating the nodes. You guys maybe will come up with some better workflows or add shortcuts for creating these nodes. Cool, so I'm going to offset that, but I don't want to change the density. Or actually, let's try that. Let's just see, a lot of things have done or happy accidents. So let's see what this gives us if we convert it back into a mesh. Cool. Okay, not so interesting. And you can see with the ISO value now we're pushing inside, and as we go deeper inside the volume, it's converting a specific ISO surface, a specific value of the data. And I don't want to change the density, I want to change the shape of it. So I'm gonna say volume sample, and I want to sample the first input, and the P is this, and it's a 3D noise. Let's add that. Cool, so let's take a look at this. Very cool. Now we're getting some more interesting details. Check a few things. So let's export this, expose these guys. Cool. So now we have some breakups happening to the geometry here. Now let's convert this back into a volume. Sorry, let's convert this into a mesh and play with this value here. I want to reach and get some cracks showing up. Something like that. And now if we increase the resolution of the volume, we should be able to get more interesting details. Let's reduce this to 0.05. Boom. And now we have a lot more details in the geometry, and you can see we're starting to get a lot of interesting blocks overlaid on top of each other. Now this is obviously the beginning and just the starting point for us, but let me let me lower this value so it's faster to work with. I want to add one more noise here. So I want to add another noise with bigger details. And I'm going to set this to 0.6. And let's take a look at the result. Cool, something like that. Yeah, it's more aggressive. You can see we have more distortion happening. Let's add another layer. Let's add 2, 2, and 2. And let's lower the threshold, the roughness, so it gives some nice wispy details. Okay, cool, something like that. And I'm not super happy about this convert here, so I'm gonna lower it to something like that. And we have the stepping effect, but we're gonna learn how to fix that very shortly. Now I forgot to do one very important thing, which is fill in the interior. And see this exterior band voxels? Now obviously the data is very different because the information is very different because we filled in the interior. And I'm also going to increase this band here, which basically adds more room. You'll see this expands about 5 more voxels outside. Yeah, it did expand, I think. Cool, so let's very cool details. Now let me show you guys one thing. Once you start playing with volumes, you'll run into these kind of issues, these kind of cases where you have a lot of floating geometry. And one quick easy way to fix that is to assemble everything and then select the piece inside and blast that and delete everything else. And now we have one single geometry. Now obviously you have to do this every time, but hopefully you guys get the idea. Now this is the kind of detail, this is the kind of geometry I was aiming to create, as well as another version of it. You can see how complex the geometry is, and it has very unique looks. So you can use this, for example, to prototype some evil or sci-fi environment that has a lot of alien-like structure, and there is a lot of information here that we can use to create very interesting shading and stuff like that. But let's go back to the volume and let's push the isosurface out a bit. And we have to be very careful with the threshold not to go super low or super high. Yeah, something like that. And this is our very first rock. And I'm going to lower the resolution to 0.04 to add more points. And this is our first rock, and we're going to start creating a bit more variation to this and do more processing in SOPs to create some more interesting details. But let's wait for this. So it's 15 seconds, 20, I think by 30 it should be ready. And if we think about how much processing is happening to this data, it's definitely a lot. Cool, so it's done. And the viewport display takes a while as well, because right now the data is in memory, and it needs some time to feed that into the GPU. And you can see once we went up high res, we got all these interesting details here, which could be, very interesting. And it's really hard to achieve that. So maybe you guys can make use of this idea, but I prefer to use higher isosurface to make that less obvious. But I really like this as well. I don't know what to do. Okay, let me assemble that. I want to select the piece at the center. Yeah, it took a while because the geometry is very heavy. And let's blast that. Let's delete non-selected. And this is everything attached together. and it's really, really cool. So hopefully you guys get some ideas from this, but I'm going to go back and change the ISO value. So I'm gonna lower this, and this is the same. I'll show you guys the final result that I had, and it's cooking right now, so it's gonna take a few seconds. In the meantime, let me change this to 0.001. But I'll show a picture of it. Give me 1 second. So this is the rock that I used. It's exactly the same one here. The next example is we're going to create these sidewalls. So this is the one, and then we're going to create these sidewalls. This ground here has a very different technique, and we're going to learn that as well. And then these are very similar to this, so we're not going to cover them. Hopefully this will be a good start for you guys. Cool. So I think we're done with this example. There's a little bit of stepping, and I think by blurring the VDB a little bit, and hopefully I'm going to show you another technique that won't generate any of this stepping, and that's the technique we're going to be using moving forward. It's not this one, but this is much easier to explain to you guys what's happening, and then once we have a good understanding, we're going to take it to the next level. Before we get started, I want to explain a few things about the copy SOP, and I'm going to create a box, and let's scale it up. I'm going to create a grid and scatter some points, and I want to copy that box into these points. Let's set this to 100, and it's copy to points. And this is the box, these are the points, and done. We're copying that. Now, in order for us to be able to vary the rotation, scale, and various things, we need to identify a few vectors. The first two, the two that are needed is the N and an up vector. So I'm going to use a wrangle attribute, and the syntax is actually very simple. This is nothing to be afraid of. So v at n, this is for the initialize, create an attribute of type vector, and the at is to create an attribute that is at the point level. The name is this n. So I'm gonna give it a value of 0, 0, and 1, and then we need an up vector. So up is equals set, and the up vector is going to be set to positive y. Cool. So now once we have that, let me check something super quick. Cool. Once we have that, we are able to do a variety of things and rotate this geometry. Let me put down a facet SOP. Let's change this to flat shaded. Cool. Don't need that. And the first thing I want to change is the scale. So I'm going to put down a randomize attribute, and this is an awesome node. We can add color, of course. Let's leave that. We can add a p-scale. You can see it's already inheriting, and it's a uniform. It's set to uniform continuous. This is just a method of distribution, and we can set the scale to go from 0.69.6 to 1.2. Then next, let's call this random p-scale, rand color. The next thing I want is the rotation. I want to rotate these guys. So I'm going to create a random attribute, and this attribute is going to be called angle. I'm going to call it angle, and I'm going to set its value to minus 360 and 360. And it's a float, so it's not a vector, it's just a float that's gonna identify how much the object rotates. And the way we can specify the orientation is creating what we call a a for float, a quaternion. So I'm going to create a point VOP, and this is very simple. The name may sound scary, but it's actually very simple. So I'm going to first import that attribute, the angle attribute, which is set between minus 360 to 360, and then I'm going to create quaternion to angle. We need to create a quaternion. Where is it? Yeah, this guy. And the angle is going to be this value, and then the axis is we're going to identify that. And then we're going to bind export this as an orient attribute. It needs to be named orient, and it needs to be a for float vector. And use this, always export this, or when input is connected. Cool, so you can see now we have that. The last thing that we need to do is convert the radian to degree. So this guy here, we need to convert the degree to radian, because this needs a radian instead of degree, and we're specifying it in degree. Now you can see the objects are rotating along that vector. So we can change the vector. Now they're rotating along that. We can specify any axis we want. We can also randomize the axis that we want them to rotate along. But for now, I'm just going to leave it at that, because that's pretty much all I care about in this case. So that's how the instancing works, and we're going to start utilizing that to create something a bit more complex. Now I'm going to start with a box as well, same like I did with the previous example, not this guy. Let me make sure I copy the box, and this is our geometry, and let's create a VDB from polygon to create a density field and use that to scatter some points. Cool. Let's increase this so we get more resolution. Let's scatter some points, and I'm going to connect the Voronoi fracture node. Now if you look at the data here, you can see we have very uniform pieces, but one thing that we can do is we can create a transform node, and we need to apply the same transformation to both in this case. So I'm going to create a reference copy, and this guy is referencing this guy, so whenever I change this, it's going to be applied to both. And then what I'm going to do is I'm going to create another copy, create action, this guy, and then I want to do the inverse. So I'm going to copy that and delete, break this connection and invert transformation, and boom, we have some very interesting elongated details. It's similar to how I did the other example as well, but this is much easier and it's more interactive. So the number of points, I'm going to change this to 100 instead of 1000. That's how much pieces I need. Cool, so let's do this. Let's assemble these guys. Create packed, and we can do something very interesting. We can delete pieces using a volume, or similar to what we did with the previous example. So here I'm going to set it to a sphere, increase this, set it to points, and delete non-selected. And now we're deleting pieces outside. And look at this. This is very, very cool detail. It can lead to some very interesting shapes. So let's scale this down. Let's scale this down a bit, something like that. And now everything is pretty much, everything has the same details. Now what I'm going to do is I'm going to put down, copy this delete here, and change it to bounding box, and let's reset this. Control middle click will reset the attributes to its default. So I'm going to select the pieces at the top, something like that. I'm going to copy this. I'm actually going to create a reference copy in case I wanted to change that, and I'm going to break this connection. It's already broken. Sorry, this guy. So delete channel, and I'm gonna change it to delete selected. So now we're isolating them in 2 groups. Now with this, I'm going to do pretty much the same thing. I'm going to create a VDB from volume, and VDB will automatically work in with the packed primitive, so it can read that, and that's cool. Let me check one thing. Okay, cool. Let's change this to 120 and turn off relax points because I don't want uniform distribution, and I'm gonna do a Voronoi fracture to that as well. Let's visualize pieces, and this is the new variation that we have. Cool. So let's assemble this as well, because now it's just geometry. So let's assemble it back. And the reason I did that is I want to delete some pieces from the top. It's too uniform. So I'm gonna copy this again, change it to bounding box, and move it to the top, and delete selected. I want to create some more breakups, something like that, a sharp ending. I don't want that piece, so I'm gonna, cool. Okay, cool. And then I'm going to merge that with this. So let's merge this together. And now we have some very interesting rock that we can, we have some very interesting base that we can use to add details to it. Now the next thing is we're going to obviously convert this into volume. So VDB from volume, and it's a fog VDB, and let's convert this to 0.2, maybe more, 0.1. And we can always middle click. I think we can go a bit higher. This requires a little bit of experience. I think 400, anything less than 450 is going to be attractive. Once you start going a little bit higher than that, it may be taking a couple of seconds before giving you a feedback. And then we're going to add a volume VOP and distort that. So let me make sure fill interior is ticked on in this case, and you can see the density. Okay, you know what, let me try something super quick just to make sure. And this option here is, most of the time it's trial and error, but it should be on. And let me look at the density first. So the density looks correct here, but I don't want to look at it like this. So I want to multiply it. I wanted to visualize it. I want to keep this on and visualize the data. I'm also going to set the exterior band voxels to 6. I'm going to put down a volume VOP, or we have this one. I'm going to add a multiply node, and I want to multiply the density. I'm going to expose this guy, and let's set it to 10. Let's go to 100, maybe 60. And let's do a VDB convert VDB, and take a look at the mesh that we can get out of that. So the ISO surface, we need to set that to a value. And let's try 40. Okay, so we'll leave it at 1, but the display is going to be tricky in this case, so we have to look at the mesh. The reason is it's not working is because the visualizer is seeing the data as one example, and then this node is reading other values that are not visible in the viewport. So it's best to look at the data using this node, and then the final mesh using this. And I'm going to delete this node. I'm going to use the volume sample and use this node to add the noise that we need. So we're going to noise up the P position, add that. And let's make sure it's a 3D noise, and let's connect that here. Now obviously you guys may notice that I'm not going crazy with the noise because we're still just starting to understand how this works, and I don't want to show you guys everything at once. We're going to be getting there very soon. So let's take a look at this. volume sample, first input, first primitive, it's all good. And let's export this. Let's export these guys. Cool. And let's reduce this value to 0.2. Okay, cool. And maybe increase this to 10 by 10 by 10. I want to get more noise. Very cool. But that's not what I want. I want much lower than that. Something like this, okay? And I want another one. And I want another copy of this, and I want to make a big distortion to the volume. So we're going to lower the volume frequency to 111. And maybe set this to 0.2. It's probably too much. Let's try 3, 3, 3. Yeah, something like that. And let's lower this to 0.6 as well. Cool. So we're getting a lot of cool details now with this. Okay, let's continue. And the next thing I wanted to do is, once we have this mesh here, let's see how much point we have. It's 251. Okay. I'm gonna copy a curve, and I'll show you. I want to use the same curve because I've made that already. So the way to create curves is, let me untemplate this. The way to create curves, you can just hit tab on the viewport, type in curve, and you can start drawing. Where is the node? Sorry, it made a new node, so you can start drawing directly. Yeah. So click the node, go to the viewport and hit enter, and you can start just drawing your curve. You can also move the points afterward by selecting the points and hitting the T key. So cool. So I have a curve. I'm going to use that, and let's delete this guy. And what I'm going to do is I'm going to copy this geometry to points, and the points are actually these guys. How much points? I have this much points, 61. I'm going to copy this guy 61 times. Now let me make sure it says pack an instance. Actually, I'm not going to care. We should be able to handle that. So let's see. Should be able to display it in a few seconds. And I'll explain what I'm trying to do. Okay, so that happened. Let's see how much. It's not very interesting. It's 15 million, that's too much. Okay, let me go back to this and lower the resolution of the volume. Now there is one thing that we did, but I'm not seeing a good effect of that in here. Yeah, this is the detail I was looking for, but I wasn't seeing that. So see how we did the fracturing of the pieces here. This is very cool, but we're missing some details here. So let's try and find a good value where we can see both. Yeah, it's fine. I'm gonna leave it at that for now, and hopefully once we understand one more thing, we're gonna be able to solve all these issues and all this stepping. But I needed to use this technique because it's the simplest one. Now this adaptivity here, we can increase that to basically tell the node to only add details where needed, and this is going to generate a much more low-res mesh, I think. How much was it before? Okay, yeah, that's good. So let's do that, and then these points I'm gonna add pretty much the same thing that we did here, but I'm gonna copy the previous values because I want to save a little bit of time, and it's just a randomized scale, rotation, and that orient attribute. Now if we take a look at this, we should be able to see a little bit of variation in the piece, in the part size. And the idea is I want to take the same rock here and I wanted to rotate it and change and copy it a few times, and then scale it, rotate it, and hopefully we'll get some interesting geometry here. Cool. So this is what I'm looking for. But now we're getting a lot of intersecting pieces. We're getting a lot of this type of stuff, but it's actually very cool. There is a lot of interesting details here. And the next thing that we're going to do, how heavy is this? Okay, let's put down a file cache. I want to cache that to as a temp, just to speed up the process. And I'm gonna save that to disk and load it from disk. It's taking a few seconds. Obviously, it's a very heavy mesh. Cool. So let's see. Sorry about that. I'm trying to do everything as live as possible, even though if I run into issues or things like that, because the truth is this is not a perfect workflow, and this is how you're going to be working. And I wanted you guys to see that in action, because having editing and removing the parts where we run into issues, I think those are critical to understand what really is going on. And even for me, I still have a lot of things to debug and issues to solve, and stuff to deal with. So if I manage to delete that node. Okay, manual, done. Let's delete that. Let's look at this. Okay, we're back to normal. And let's read the mesh. Looks like it didn't save the file, so I'm hitting save again. And the basic issue we're trying to solve here is if you saw the pieces before, there's a lot of overlapping, there's a lot of interpenetration between the parts, and I want to create a seamless geometry containing everything together. Okay, so we're back. Okay, cool. How big is it? Okay, cool. So let's create a VDB from Polygon again. Cool, and let's convert this into density, and let's lower the resolution to the amount needed to capture all the details, so 0.01 maybe. And I'm just going to convert it to volume one time and then back into a mesh. And by doing that, we're going to blend in all the details together. So I'm going to lower this even further, 0.04. We're going to blend in all the details. When we did the copy, there's a lot of pieces interpenetrating together. There's a lot of interior faces and stuff, and all the geometry we don't need. So by doing a volume of all of that and then combining that together and converting it, we're going to leave only the data that is at the shell. At the same time, we're also going to blend in everything nicely in terms of edges. We're going to seamlessly blend all of that. And to save time, I'm not going to add any post-processing for this volume, just going to convert it back straight back into a mesh, and it's going here. So if it's not too heavy, then I'm going to convert it straight away, but I feel like it's going to create a very heavy volume. So let's see. And there is always a delay, depends on the graphic card that you have between Houdini creating the data and feeding it back. So it's not a crazy volume. Let's do a VDB convert. Let's convert that back into a mesh. And once we start getting into dealing with heavier volumes, any process that we do is going to cost time, so we have to be very careful. Now I set the ISO surface to 0.001. Okay, let's set it to 0.1. Cool, so now we're getting some nice details put together. And we have a very interesting rock formation. Actually, if we light this, let me go back and change the light, so maybe that to 2, and let's make a copy and rotate this again. Okay, cool, and let's turn this off. So let's delete this off, set it to 0, and this is still too bright, so let's set it to 0.4. Okay, cool. It's still too bright for some reason. Okay, so you can see we have very interesting rock formation here, and let me delete this animation and rotate. You see we're getting a lot of cool stuff, and just by using the Voronoi, by converting it into volume, adding a little bit of displacement, we're getting a lot of cool details. Now obviously we're going to learn a couple more things that will make this even better, and hopefully by now you guys have an idea of how this system works. So the next thing I wanted to add is I want to add details that are uniform to all this. Okay, right now each one of them have the same details repeated. I want to add something that is world space detail. So I want to add some kind of erosion applied to all of it. And I'm going to do this in a point VOP. I'm not going to convert this into volume or do it in a volume. I want to process these guys as points. So I'm going to create a point VOP, and I'm going to generate a noise and add that. And let's add it to P. And this time, again, we're just doing points processing. And there is still room for this. There is still a lot of things that we can do to make this look even cooler. So we can set this to 0.5, 0.25. You can see by just doing that, there is a very interesting distortion happening. And because of all that nice blending happening, we get some very cool details. So this noise here helps a lot to make this non-uniform. Let me change this back to 1 as it was, and let me add one more of it. So we'll set it to 3, and maybe the value 0.6, something like that. And then I want to add one more. So this one, I want to add, let's say 6, and 6. I want to make a fine noise, but I don't want it to be uniform. I want it to be stretching along a specific axis. So I'm going to set the Y to 60, and this is the kind of details I'm looking for. I'm going to set this to 0.2, some kind of wind erosion. Yeah, this is the effect. And let's set it to 0.2. And because we're doing it with these noises, it's also getting disturbed. So I'm not going to do it here. I'm going to disconnect this guy. I'll explain why in a second. I'm going to disconnect this guy. and we need to do it afterwards. So I'm gonna copy this, and I don't want this new noise to be disturbed in any way. So I'm going to delete this. I'm gonna add another add and connect this guy. Cool. So you can see now we're getting some very cool lines across this. Okay, let's do something else. Let's try something a bit more complex. How long is the... Okay, I'm going to show you one last thing, which I think will be a bonus. And this thing is, this geometry has a normal, okay? And if we can use that normal information to create very interesting masks, I'm going to create a dot product node. And dot product basically, let me explain it briefly. So we have a surface like this, we have a camera, okay? This is the normal facing the camera. This is the direction of the camera. When we look at this straight and run the dot product between this normal, which is the surface normal, and the vector of the camera, we get result of 1. When we run the cost product between this normal and the camera, we'll get 0. And that's how a diffuse shading is computed. But this will give us a 0 to 1 value. So we can take the normals of the mesh, and okay, let's do it here. If we take, you know what, I don't want to do it here. I want to do it in the next level. Let's do it. We don't have to, but I want to do it here to explain a few things. And I want to compute the normals again, make sure that I have an up-to-date normal that has all the details here. Cool. So let's dive inside, delete all this, I don't need it. And then, excuse me, and then I'm going to compute the dot product between n, the normal, and an up vector, which is this guy. And if I connect that, you can see we have a mask showing only the stuff pointing upward. This is very cool. What we can do with this is we can mask details. So for example, we can mask, let's go back here, and let's say we liked this mesh. I'm going to create a rest. This rest is a copy of the point's position at this point, okay, before they get modified with this interesting modifier here, the erosion thing. And I'm gonna import, and remember we're processing a very heavy mesh. I'm gonna import the rest, which is the position of the points at that state. And if I put a mix node between the current position and the new position, and let's visualize this. Let's turn this guy off, and let's visualize this. Cool. So let's try set this to 1. Boom. We don't have any. It's 100% the result. This result. And if we set it to 0, it's 100% the deformed one. And we can use the dot product to drive this. So I'm going to connect the result into here, and now we're blending the details between the deformed one versus the non-deformed, and we're removing the details from anywhere where it's pointing upward. Now let me add a multiplier, because I noticed that the map didn't have a lot of details. I'm gonna set this to 3, 4, and that is creating a bit more interesting details. You can see already. Now obviously it's not very interesting to see it being applied throughout the mesh the same way, so I'm gonna do one more thing, and I am just doing them in a separate point VOPs to make it easier for you guys. Okay, so I'm going to delete this. I don't need this guy, and what I'm interested in at the moment is a vector to float, and I want to use the height. Okay, so the height of the y-axis should give us a black to white ramp, okay, from 0, and I want to use this to drive the blend. So I'm gonna connect this guy, and you can see now if we go, let me remove this. can see now we have very interesting blend of details between the bottom and the top. And we obviously can add a local attribute to store the original position before they get deformed, so we have a local attribute per point. Now this is getting negative value, so it's pushing further, so we need to clamp the vector to float so it doesn't go in the negative range. Yeah, something like that. It clamps the negative and the positive as well. Cool, I think that's pretty much it. And one quick note is if we dive inside this, which is very, very interesting, we don't have any floating details. We don't have any issues with the geometry. And this is very powerful because we don't have to worry about cleaning up or doing anything with this mesh. It's perfectly ready to use in production as it is. And it's perfectly quad mesh. So we can just use this with Arnold. Now, once we have the mesh ready, it's getting too long. Yeah, it's fine. I'm going to continue. So this part is, let's do it in a separate video. So yeah, I think it's getting too long. In the next video, I'm going to show how to export this using the pipeline tools and how it's going to work. In this video, I want to go over a few things about the pipeline tools and what we've set up to explain the advantage of them in more details. Now, there's the high-res version here, and if we dive inside, it's importing nothing. So let's make sure it's importing the correct data. So I need to dive here and connect that out model into the proper node. So this guy here. Cool. And let's go back up. Now this is ready to be rendered and everything. So let's make sure the camera, that's cool. And let's make sure the render cam also sees something interesting. Okay, good. So the high-res version is this guy. We don't need to change anything about it. It's 4 million, that's fine. Now let's create a low-res, and there is a very simple way to create a low-res mesh in Houdini, and this is what we're going to be using actually throughout the course. It's called a poly reduce, and if we connect that, we tell it to just, you know, keep 5% back, and it will do its best to try and give us 5% back of the mesh that represents as close as possible to the high-res one. And this is a very, very interesting node. Now, it has a little bit of limitation in terms of attributes that are not going to be inherited properly and things like that. But hopefully they'll be improving this version in the next few releases. And for now, we're just going to be using it to generate low-res meshes and use them for preview and or for real-time rendering. So I'm waiting for this node. It's going 40 seconds. And again, we're dealing with the 4 million points. So this is perfectly fine in terms of the time it takes to give us back a proper mesh. And then once this is done, I'm going to cache it. And then I'm going to use the export tool to basically export this, generate the S file, generate the high-res geo and the low-res, and then I'm going to import them and show you guys how that works. And it should be done soon. We'll give it 15 seconds. And then in the next example, and then once I'm done explaining this, we're going to start looking at a little bit more advanced techniques with the volume displacement and hopefully create something more complex. Cool. So let's see, 200,000, and it done a pretty good job so far. I didn't have any issues with this. So let's this is actually still low res, so I don't want to change that because it's going to compute it again. So I'm going to set this to I'm going to create another poly reduce, and it's going to poly reduce this version, and that's much faster. And now how much we have? 40,000. I think that's reasonable. Let's connect this, and let's put down a file cache and call this geo low-res cache temp. Let's connect this. Okay, cool. And now we have our high-res and low-res and let's go to the out. And all we have to do is, everything is set up. We don't need to worry about anything. It's the base variant. I just want to change the color of the asset so we know that the shader works. I'm gonna set this to that color, and then let's hit the export button. Render to disk, and it's gonna take a couple of seconds to export everything, and call Arnold to export the geometry as an S file. I think that's the part that takes the longest, but it's reasonably fast if you think about what it's doing. It's exporting 4 million points, and then it's done. So I'm gonna save this and create a new scene. And with this new scene, I wanna use the Rebelway tool. So import all asset. I'm not gonna use that. I'm gonna create the Arnold procedural RW. And what was the name of the asset that we made? Let me check that. It was called this. Now the constraint of the R&D only is being ignored when we use that through the tool, but this here should be fine to use. So I'm going to copy that base and set this to version 1, and done. We have our asset. Now there's a little bit of points here that we should have deleted them, but it's perfectly fine. I can change this to the high res, and it should display the high res version. That's our high res mesh. Cool, and then we should be able to render this nicely. Now we can again go back to the original scene, work on this, export the cache, version up, and then just change this number in the main scene, and we should be able to get all the data in nicely. In this video I wanted to talk about the edge displacement effect, where we take a low-res geometry and try to add more details. This is something that we see a lot done for destruction, to, let's say, take this low-res geometry and add edge displacement here, as well as interior details. This technique that I'm going to show you is can be applied to destruction as well as to anything that is not destruction, and most of the method that are out there will not work with the stuff we're doing, because what we're doing in this case is we're deleting exterior geometry and we're dealing with interior faces all the time, and there is no exterior or interior faces that we can work with. So I want to show you guys a method that works with any kind of geometry. And let's say this is our geometry here, and I want to make edge details, but I don't want to change the surface. I just want to displace wherever there is an edge. I want to displace that. So the first thing I want to make sure is I need to fuse this. Or actually, before that, let's add division. And the technique here, the technique I'm going to explain is based off skin sliding method, where we see this used in character and skinning, where you take an existing geometry and slide it along itself. And we're going to create something similar to that. So let's see. Let's set this to 0.1. And it's a packed primitive, that's why we're not seeing anything. So let's unpack the geometry. And I've did this quick Voronoi setup and removed a piece from the inside, so everything is inside faces for this guy. Okay, so now we have more details, and let's just 0.1, 0.01 for all of them. So let me copy, paste relative reference. Okay, cool. So we have enough details, and I'm going to fuse all the points just to make sure that everything is connected together. Cool. So let's talk about how this is going to work. Well, if we put down a facet sub and compute the normals, we see that, and visualize the normals. Actually, let's set this to 0.2 so we have less. Let's see. The normals that we have right now is pointing outward, out of the surface from the point outward. And what we need to do is we need to leave this face intact, and we need to only affect this guy. Well, how are we going to do that? Well, we can take the normals of the surface and compute a new vector based on that. And that new vector, we can use to displace the point. We're going to be affecting these points. We're going to be affecting these guys, these points here, but we're not going to be shifting them to move on a plane that is different than this. And what we're going to do is we're going to create a new 3-axis system, basically it's similar to matrix, but a 3-axis that we're going to use to shift these points along. And let me explain this here. So let's say we have two faces. This is the normal of the first face, and this is the normal of the second face. Okay. Now, what we need to do is we need to offset these points in a way that they move along this face. Well, we can easily compute that. We can take the normals and do a cross product with an up vector, and that will give us the tangent of the surface. It will go up, it will give us a vector that goes from in this direction. And same here, will give us a vector that is parallel to the surface. Great, so we can use this direction here to take this point and move it in this way. So we have one axis, but we're still missing another one. We want to offset things in the up vector, but relative to the plane. So we can take this guy, the result itself, and do another cross product between this and the original normal. And you can see there is a plane here that is formed already. And by doing a cross product, we're going to get an up vector like this. And same for these guys. This is the plane. And by doing the computation of the cross product between this and this, we get another up vector. Now these are the two vectors that we need. We don't need a third one. This is our space that we need to transform the vectors along. And this is the same for the guy. So we're going to take the points and offset them along this way and or this way, and apply a noise to move things back and forth. So let's create a point vault. And let's go back to 0.05, a bit more, 0.02. Okay, and now we have our normals. Let's dive inside. Let's create a cross product. Now if we take the normals and just leave it at that and do a cross product with the up vector and visualize the result, we have what we call the tangent. Okay, and if we take this tangent and let's normalize it so it goes from 0 to 1. If we take this tangent and add it to P, just add it to the points, we're going to be moving the points along that vector. So let's turn this off, and right now the result, the offset is too high, so I'm gonna add a multiply by a constant and set this to 0.01. Let me turn this off and so you guys can see the result. So I'm gonna start increasing this. You can see how it's moving. Okay? Each one, we're not changing the data here. Everything is moving along that vector. But we don't want just that. We want another vector to move them up and down. So let's connect N to view it again. And let's set this to 0. And now we're going to take the cross product of that and do another cross product with N between the result and N. And let's compute the normalized vector and view that. So we have the other vector and see how it is aligned to the surface. And these are my two vectors. Okay, so now if we take this guy and let's multiply a constant, let's copy this, paste them, paste relative. I want the same multiplier and I'm gonna add that. And let's add this one as well. Let's remove N. And now if we change this, we should see the points moving. Okay, see how they're moving? They're sliding along that surface. Now obviously we cannot push this to an extreme because it's gonna start to ran into intersection issues, but we can easily use the result as it is. So if I create a noise based on P and multiply all the results here, so let me delete this guy. I want to add the two vectors that we've created together and then multiply those by the noise, and I want to add all of that back. Okay, into P, and let's expose the noise, and let's set this to 1 and just use the noise multiplier. Okay, let's reduce this to increase the frequency. And you can see let's compute the normals again just to get a better idea of the surface. Let's hide this. And you can see how the surface itself is still intact. We're adding Z here, so I'm going to create a vector to float, and I want to zero out the Z axis because I don't want to change that. And here, by adding the noise, by multiplying it, actually it should not. Yeah, let's just let me try this real quick. Float to vector. And let's see. Cool. So I think we need the Z to be 0. Yeah. So we don't want to change the Z axis, and you can see already that we're deforming the edges, but we're keeping everything else intact pretty much. And this is the technique I want to use to deform the geometry. Okay, this is what we're going to use to break up the edges, and this will simply work with any method. Now, the geometry, of course, obviously is a little bit deformed overall, but we can smooth that out if we needed to, just a little bit. And we have to be careful with. Actually, I really like what I am seeing, but just in case, if we needed to improve this a little bit, we can add a smooth and use the scale by curvature, and this tends to clean up the geometry quite a bit. And let's add more details. Let's set this to 0.05, so we have a lot more details. Cool, so that's great. And let's see, yeah, this kind of stuff is, unfortunately, there's nothing much that we can do there. And then we can do a VDB from polygon and generate a high-res volume out of this. Let's do 0.3. Okay, cool. And let's convert it just to see what kind of results we may be getting. So back to polygon, and let's set the isosurface. Increase it a little bit. Something like that. And now we have very sharp edges, you can see there. But the overall silhouette hasn't changed a lot. Cool. I do think that we need to add the Z because that's what I have, but it shouldn't matter. I mean, in the end, in the final example, I'll check the file again. Yeah, I think it's working. I think that's what this is giving us. But basically, if we compare this with where we started, which is this guy, yeah, this is what we started with, and this is the result. And it's going to add tons of details to our geometry. I think that's pretty much it for the edge displacement. We're going to be using this to create our high-res cliff element. So now we're going to take another look at creating one of the high-res assets that I showed, and this time we're going to create this guy, this one here. And I'm gonna use an existing setup to start the geometry because we already covered the method, and this is what I'm going to be using. Actually, let me create a project first. So let's create asset AAC workshop, and then let's call this standing cliff live. Yeah. And then let's create the project. Not that one. This guy. Cool. So the startup geometry is very similar to what we've done in the previous example, but I wanted to keep the same input, and I didn't want to waste time. So let's see what we have here. It's basically a box. I deleted some parts from it, and then I added the edge displacement. Actually, the edge displacement I'm going to create together. Cool. So this is the geometry, and it's very similar to what we've done. So we'll start up with a box, scale that down, and do the Voronoi, extend it back, add the division, assemble it to convert it into packed primitive, delete everything except the outside, and notice here how I'm getting these. I'm reaching out to the boundaries of the box to get these nice flat shapes, and this one, for example, to add a little bit more breakups to the silhouette. Now I'm going to isolate some parts at the top, and I'm going to also delete everything else except the top. I'm going to blast one shape here and merge that back with the parts that I'm going to add details for. And then I'm going to subdivide that, Voronoi fracture that again. And let me preview that with colors. So this is the new result, just more points. And then we need the inside faces are not subdivided like the exterior, so we can easily isolate that using the groups. So I'm going to isolate the interior faces versus the exterior, and divide that. Now there is faces that are being subdivided twice. I'm not going to worry too much because once we go into volume, and plus I believe I'm going to delete that part, so I'm not going to worry too much. Now everything is subdivided, has the same details, and let's continue. And then I'm deleting the top part to create more breakups at the top layer. Okay, and then merging all that back together. And last thing, I want to, instead of having this shape being too uniform, I'm going to add another delete and remove some parts from here. So not the entire graph, just one delete node. And let's see what we get. Still going through the divide, though this method should be much faster. But because of all the fracturing and stuff that we're doing, it's taking a bit of time. And once I have that, I will cache the geometry so it doesn't keep caching it again. Cool. So I just deleted some parts from here. This is the original. This is the second one, and some from here. Actually, I'm not liking these guys too much. Yeah, something like that. Let's leave it at that, and then that's fine. And then let's put down a file cache just to save it to disk, and then call this temp cache. I'm not too worried about the name at the moment, so let's do that. And then the next part is I want to add edge displacement. So we have all the details we need. I'm going to unpack this because it's packed primitives. Okay, and then I'm going to fuse everything, and then I'm going to compute the normals, make sure that I have the right normals, and maybe I think we can leave the normals. Let's try without the normals and see, because these guys should also be, yeah, let's try both. Let's try with the normals and without and see what kind of results we can get. And then let's put down a point VOP. A point VOP. And let's do like we did in the previous example, so cross product of n with an up vector, normalize that, and then cross product of the result with n again. Let's normalize that, and let's multiply. They're both normalized, so I can add them together, and let's multiply all of that with a noise. So let's create a noise. And let's multiply all of that with the noise. I'm gonna start with a 1D noise and see what we get. And then let's add this to P to displace the points finally. Let's take a look. It's messed up. So let's export all these guys and tweak the values a bit. Okay, so first of all is the value. Yeah, without the noise is going to give us better result. Yeah, let's try that, and let's increase this. And let's add another facet SOP. Now the parts, the only problem is we may be having the parts that have been subdivided twice, like these guys, will cause a little bit of issues, but everything else should be fine. And look at this is the kind of details I'm looking for. I'm not changing the silhouette, I'm not changing the main geometry, but then we're adding a lot of cool details. So let's play with this. Let's try a 3D noise. Yeah, I think 3D noise would work better. It's definitely changing the faces a little bit, the silhouette a little bit, but not too much. The main difference is in the edges. So we're gonna go with that. And at the moment, I'm gonna leave it at this point and create a VDB from Polygon. And I realized that the fill interior was giving me some issues, especially with the bending. I'm gonna leave it off. I'm gonna leave it off in this example and see what we get. So VDB convert. Let's convert it into a volume. Change this value a bit. Okay, cool. We're getting some interesting details. Now let's start playing with the volume. And I'm gonna create a volume VOP. Let's see how much details we get. Yeah, let's increase this a bit more to get more resolution. And let's add a volume VOP. Let's create some noise. Volume sample. And the noise, and let's connect this again to density first input. That's good. Let's export these guys. Okay, let's change it to a 3D noise, and let's go up. And let's take a quick look. Yeah, we're getting a much more interesting result now. Let's change the values here to something a bit more interesting. That's too much distortion we're getting, so let's lower this guy. And let's set the octave to 4 instead of 8 to get less details, and let's change the noise to simplex instead of per lane. So we get it gives us a range between 0 and 1. Okay, cool. And let me try and change this to 1D. Yeah, I think I'm gonna go with 1D for this example to match what I had before. It's definitely a matter of trying which one works better for you guys, and it's just trying a variety of combinations of all these noise to create something interesting. So let's set this to 3. Yeah, I think this is working better. And see, with the 1D noise we get these kind of flat faces because the noise is not being applied to everything all the same way. And it definitely adds a lot more interesting variation to the surface. Now I want to push it a little bit in. Maybe we'll do that when we go to high res mesh. Okay, cool. So let's add another noise. Okay, let's add another type. So I'm gonna copy this. And I'm gonna dive inside. And I'm going to change the noise this time. I'm gonna use a turbulent noise. I'm gonna change it to 3D, and the type I'm gonna leave it to alligator. And let's expose these guys. I'm gonna give this a name. Honestly, it's just combining different noises together. And I'm gonna copy this and call it noise. Okay. So let's take a look. It's too aggressive, but it's creating some really cool effects. You can see it here. That's very, very interesting. This is very interesting as well. Anything basically where it adds a volume or pushes it out, it definitely creates a lot more depth to the asset. Now I think it's set to, yeah, it's a 3D noise. Cool. So let's tweak the values a little bit. Let's set it to 3, 3, and 3. And let's lower the frequency to 0.1. Sorry, the amplitude. Okay, cool. Yeah, I think it's working. Let's add more noise to this. So I'm gonna copy the, 1 second. I'm going to copy this first one. And this time I'm gonna change it to 3D noise. And let's see what we get. Okay, we're destroying it too much, so let's try something. Let's try adding finer details at a lower frequency, at a lower amplitude. So something like that. But then let's lower the values to 0.1. It's too much. Yeah, something like that. And maybe even more. Let's go 40. And let's increase the roughness so we get more sharper details. Now obviously this is too uniform, so I'm gonna add something else. I'm going to copy, let's add another noise. And instead of using this B itself, the point position as it is, I'm gonna add a noise to it before it goes into the noise. Okay, let's add a 3D noise, and we don't have to expose this, we can just tweak it here. Let's take a look at the result. Boom. You can see how awesome the distortion we're getting is. And this is really cool. Look at the details here. This is really, really cool. I think it's much better than the one I did before. So let's increase the frequency maybe. Okay, and let's lower the amplitude a bit. Okay, cool. And I really like this noise. I really like the distortion happening to the mesh. And I'm going to copy that. I'm going to copy that and use it as it is. Use the noise itself. So let me dive inside. And instead of this, I'm going to use this noise. And let's expose some settings for us to play with. Now obviously some fine details are going to be much harder to see if we're using low res geometry, and I need to do one test where I go high res and then go back and tweak again. So this is going to be, let's lower it. Okay, cool. And let's add a little bit of offset so it's not the same frequency as the other one. Cool. Yeah, I think it's working pretty well. Now the last thing I want to add is, where is it? I want to copy this noise here and add it one more time with very small, with very low frequency. So 20, 20, 20. Make it sharper, and let's add 0.2. Just a tiny bit. Okay, cool. And let's try and play with the volume. You can see we're getting a lot of interesting details. Now, how much details we have? I'm gonna go and increase this. Hit pause because it's gonna take some time, and then come back. So let's see, what value do we have? The next value, so the high res value I had before is this, and I'm gonna change it to 0.25, 0025. Hit pause, and then we'll come back and tell you how much it took to compute this. So it's done. I think it took about 2 minutes to compute all of this at this resolution, and we have 378. We have about 60 million voxels, and the final mesh is 2.9 million. And let me show you guys the details. Okay, so this is the final mesh. Let me increase the geometry display, the anti-aliasing, so we can see it better. And this is the quality of what we have. Now look at all the curvature, look at all the details with, it's not just a height, it's not just pushing the data. Look at this. It's creating cavities and creating a lot of overlap. I think this is pretty much impossible to sculpt and by hand, or even think to sculpt these details, because our brain is, we are used to sculpt, add stuff or remove stuff. It's hard for us to carve in details like this or imagine them. I think it's really hard unless you're very trained to do this kind of details. I think it's not a very easy thing to achieve, and I think I pushed the noise too much. I'll show the other result in a second, the original one. I think I pushed the details too much, but I really like what I have. I think there is a lot of interesting behaviors to this, and you can see how awesome and detailed this rock is. And this is, I mean, it took 2 minutes to compute this, so it's really fast. And the only thing I'm missing right now that I would like to see a bit more is the cracks between the rocks. And because of the noise, because of the level that we pushed the rocks at, it's yeah, we're not seeing that too much. But this, for example, is really cool. All these details here, even though we're not going to see them, the volume change, the silhouette, everything about this rock is very cool. This part here. Now there is definitely a lot of tweaks that needs to be done, but having lines like this, having sharp, these kind of behaviors are very, very interesting. these guys as well. Okay, so let's add something else. Okay, the next thing I wanted to add is I'm going to select this. That's a bad idea. Actually, it worked. So there is a little bit of floating pieces. I can do a assemble and select that. The reason I didn't want to do that because it will create a blast node with the list of all the points, and that's gonna add to the file size. So if we do an assemble node, it's gonna take a couple of seconds to assemble this, and then we can easily pick one shape and delete everything else. So it's taking 1 second. Okay. Yeah, so I see all that left over from the geometry processing and the VDB conversion. So I'm going to delete that. And I'm going to show you guys one more thing. Now this guy here, the VDB convert, we can obviously change the value to decide how far deep it goes inside the volume, how far what level it considers to be the limit of the volume, which is this guy. Let's set it to 1. Yeah, it's bringing in more details. You can see we're going to get a lot more, we're going to carve in deeper into the volume field itself. And this is also very interesting and really hard to get. And it may be more suited for something along the beach, like at the shoreline, or where there's a lot of waves hitting it that can cause this kind of erosion onto the mesh. Let's try 2. Nothing at 2. Let's try 1.2. Yeah, I think that's the max. Cool. So I want to show the other geometry, which is here. It's pretty much the same, just a different noise. And what I like about this that I don't see in the other example is these crack lines, and that's because of the noise. We pushed too much the pieces between each other, and so we lost all the information and we have to go back and tweak it. But other than that, I really like the new one as well. I think it has a lot of interesting characteristics. Let's see. I want to show you guys something else. So let's do a measure node, and let's connect this. Let's connect it here. And let's make sure to unpack the geometry. Actually, you know what? Let's yeah, dealing with heavy geometry definitely has its issues. So let me copy file cache. And let's save this to disk. It's gonna cook the chain again, so it's gonna take a minute or two. I'm gonna pause and then show you guys another tip. I think I showed you this, but I want to do it again just to see what kind of effects we can get with it. Cool, see you in a bit. Okay, so I have the file saved, and let's read it back in, and I want to compute the curvature. Okay, let's leave that as it is, and let's take a look at what we have. Now obviously we're not gonna see any difference because it just made a curvature attribute. But what we can do is we can put down a color attribute, color node, and set the type to be, once it comes back, ramp from attribute, and the attribute is going to be curvature, and the range is going to be 0 to 1000. Now this is going to give us an indication as to, obviously we can see it, but it's going to give us an indication in terms of details, how much details we have in geometry. And this is displaying it as points, and it's not actually very accurate, and it's much better to do it in real when rendering, but you guys can get an idea about how much details we have inside the geometry. And this information can be very useful for a variety of things, to scatter pieces, scatter geometry, or drive shaders to do to change the materials and things like that. For example, you can see we're not touching the edges there. And we can isolate a lot of interesting parts of the geometry. Now, the idea where I mentioned that you guys can create textures in week 3. Now let's say this is our geometry, and maybe if it didn't have, or maybe even if it did, if we have flat faces that don't have a lot of details on them, we can paint maps in here in Houdini and use those as masks to drive different shaders. For example, let's say all this area here, we can paint a mask. It's gonna be a little bit slow, but let's try put down a paint node. We can isolate certain areas, and then with those extra displacement that we've created in week 3, we can add cracks to various parts of the geometry. We can add small details, and here I think in one of the examples I added extra displacement created with the terrain tools and used those to add moss in this geometry, and a variety of other rocks that are pushing out of the mesh. So yeah, it's going to be a little bit heavy to paint the colors on these, but I think we can do it. So let's try. Yeah, so it's not too bad if you think that what we're working with here. So we can paint any attribute we want, and then say import that in the shader and do any masking with that to add displacement or anything like that. Okay, so I think that's pretty much it for this video. Now we're gonna move on to talk about how to really do volume displacement, because all this is an intro to properly doing volume displacement. Hopefully you guys have a very good understanding about the advantage and how to use it. And in the next videos we're going to start talking about a new approach and the next level of how to create rocks and things like that in Houdini. In this video we're going to start looking at volume and side distance field and understand how to use them in Houdini and what's the advantage of using them. We're also going to be looking at understanding what the gradient is and how to use that information to properly displace volumes inside of Houdini. And before I get started, I wanted to show a quick alteration of the asset that we did. The only thing I did, I deleted a couple of blocks, a couple of pieces here at the top, and then removed one part. And this is a low-res version of it, so it cooks faster. You can see already how much cool details we're getting. I really like the connection here as well. And there is an unlimited amount of data. Actually, I can show you guys if I can find the data quickly. Yeah, let's see if I can find it. Yeah, I don't have the render, but basically I made a 10 different versions of this by just changing the seed of the noise in the scatter here and the noise that we used at the scatter at the top, and that gave me multiple different versions that are very unique. Cool. So let's see if we can cancel this. We can. So let's get started. And what I wanted to explain first is something. I wanted to explain the SDF. And so when we have a volume, we can either choose if it's a fog or a surface. And what a surface mean? Is it a surface? Let me check. distance, yeah, if it's a distance VDB or a fog VDB. Now, a fog VDB will just get a density filling this entire volume, and it will be denser at the center and less dense around the edge. And this is what we call the isosurface. That's the limit of the volume. Now, with an SDF, if we take the same data and instead of using a fog VDB, we convert it into an SDF, the first thing that we're going to notice is the display is going to be different. It's going to look like an actual surface. And we're going to be able to push and pull the data much better because the SDF knows more about how far the points are inside of the volume as well as outside. And we want to be running into the stepping issue that we were seeing before with the volume. So the truth is, the proper workflow to do volume displacement is to use science distance field, is to use SDF. But I didn't want to overcomplicate things for you guys. I want you guys to get comfortable with seeing volume as it is thought of, as a volume, basically transparent thing. And the true proper method is to use an SDF, and that will solve all the stepping issues and will allow us to do a lot more things. And we also don't have to convert the data into geometry. Cool. So now once we have the SDF, there's another thing that I wanted to talk about. We have a volume. If I can make a sphere. We have a volume, and let's say with the SDF, it allows us to know how far we are inside the volume. So if we place a point here, we can know how far it is from the surface. Okay, we can place another point, and it will tell us how far it is from the surface. Now, volumes have another property, and for example, let's say we have a box. Okay, and we want to displace this box, and it's a volume, and we want to displace this volume. Okay, the way we're going to be displacing it is basically randomly. We're going to take P and just add values to it, either along a specific axis or randomly. Now, when it comes to maps that are Worley, that are 2D maps, they just give us black and white value. How are we going to displace B? We need a specific vector, like we did when we did the sphere example and used the Worley map. It gave us a stretched tube. The reason for that is because all the positions are being offsetted using the same value, and that is a limitation. We need to create a vector that we can displace along, and that vector with volume is called gradient. And what the gradient is, it's basically at each voxel, it can tell us how far it is from the surface or the direction that this voxel needs to move to reach the isosurface. And a gradient in a volume is basically normals on a surface. And that's how we need to think about it. Now let me create a sphere and illustrate all of this. I'm going to create a volume VDB from polygons, and what we've done before is create a fog VDB, and let's increase the resolution, something like that, so we have more details to work with. And let's increase this to have nicer geometry. Cool, so this is the fog, and I'm going to copy that, and instead we're going to change it to surface. And look at that, it's displaying it as if it's a geometry. Now let's lower this, and the lower it goes, the more you can see the voxels in there. Now Houdini has a very clever thing where it can figure out how to display this as a surface, because it knows it knows about the gradient information. Now we can stream the gradient directly and use that to displace this data, but I'm not going to do that. I want to show you guys a different method that will compute the gradient, and this is what I'd like to use. Now with the VDB itself, there is also fill interior, and there is what they call the exterior band and interior band. Now if I hit W, you can see there is only data in here and inside. There's not many bounding box around this, and we need to expand this a little bit because we're going to be displacing this. We need a little bit more room. You can see the interior is going in. We need more room so that we have enough data to push stuff in and out, and we're gonna see some very cool stuff soon. So let's create a volume VOP. Okay, and let's do our typical displacement. And let's do a volume VOP, a volume sample. And let's connect the first input. And yeah, that's pretty much the same. Let's add a noise. And let's add that to offset P. Now I want the noise to be 3D. Okay. Cool. So let's connect this to density and go up. Well, nothing happens. Now why is that? Well, if you middle click, it says surface. Okay, here it says surface, it doesn't say density. Now we saw that we can remap, do custom binding for the data. Okay, and what we can do is we can come in here and say to untick auto bind and create a new binding for the primitive density, and we're going to call it surface. And by doing that, we should be able to see noise on the surface. I'm going to reduce this. Let's try one more thing. Let's try surface and call this density. Yeah, it's working now. Let's try 5. Cool. Let's try 1. And I think the noise is still too big, so let's lower this even further. And let's increase this to 10. Okay, cool. So I'm going to copy this and paste relative reference. And let's lower this even further. Interesting. We should see more changes. Okay. Now there is a limitation that once we do this, we have to keep binding everything. And what I prefer to do is I'm gonna take on auto name, leave that to be the default, and the correct way is to leave this connected, we don't care about that, and bind export this as a separate thing. So we need to call it surface, and now we're displacing our volume. Now let me take a look and see why that is. So we're adding the 3D noise. Yeah, everything seems to be fine. Let's create another noise. Okay, yeah, something is up with this noise. Maybe the frequency is too... Oh, I see. Sorry. Yeah, it went too low, that's why. Yeah, I need to go... Yeah, so it went too low. But let's use this for now, it's fine. Okay, so look at the result already. And just to reiterate, we don't do the auto bind, just export. Do a bind export and set the data to surface. This name has to match this name. That's all. So we're reading the primitive number 0, and I can change this to actually have the correct name, so surface. And now we're binding exporting that. And look at the result that we're getting. We're actually seeing the surface itself displayed, but it's an actual volume. Now see how it's getting clipped here? And that's because of the exterior bands. So we need to increase that. And the higher this value is, the slower it's going to be, obviously. So let's set that to 50. Okay, cool. Now we have something very, very interesting. Let's set this to 50 as well. And now we can take this and do a VDB convert VDB and convert it into a mesh. Pardon me. And by doing that, we're not going to have any banding issues. We're not going to have any isosurface. Actually, we don't have to worry about this value anymore because it knows much more details about the surface and where the actual geometry starts and ends. And we can push, this is the other thing, we can push inside now and look at that. We can create some really cool stuff with this technique. Okay, and honestly, you guys have to play with it. There is just so much that this method can create that I haven't explored yet myself. So the next thing is, let me copy this. Let's leave it at that. And the next important thing is the using 2D maps. So let's say I have a whirly, and we have. And let's lower this a bit. 4. And let's say we have a whirly, and we want to subtract the f minus f2. Okay? And we want to add that. Now, how do we add a float? Let's take a look at the result. Let's maybe add a multiplier here. And let's turn on computing again. Cool. So you can see we have a constant. We can keep pushing this, and it's going to keep going in one direction. And let me test this with something else. So we have a sphere. Let's create that toy, the rubber toy. Let's template the sphere and make sure the rubber toy is at the same scale. Okay, and maybe increase it a bit, something like that. And let's convert this. Let's use the rubber toy instead. Okay, cool. So now we have this, and let's take a look at the result. Well, it's gone. Like, we don't have anything left of that toy, and the reason for that is because we're offsetting p along one vector. It's everything. All the axes are being multiplied by the same value. Okay, let's convert this into a mesh and take a look. Into a polygon. Cool. So it's definitely creating something, but it's not working the way we want it. Now, what we need is we need to compute the gradient, and that's what we need to use to offset this data. So let me show you this. VDB analysis. Take this field, and the operation, we want to compute the gradient of the surface. And look at this. It says gradient. It expects a scalar field to a vector, and the scalar is basically a float, and that's what the surface field is. And then we can say I want to create a custom name, and I want to give it gradient. Now we're not going to be able to visualize this because there is no way to visualize it without having a density field, and we don't care about that. We don't care about the values. We just need that information. Going to plug it in, and now we have a second input. Now how do we read that second input? Well, we can use the volume sample. Now let's connect this to P. It has to be the original P. Okay, let's move this. It has to be the original P, and then we're going to change it to second input, and the name is grad. Okay, and now instead of adding this constant value here, I'm going to multiply the value. Actually, sorry, we're not going to use volume sample because the volume sample node can only sample scalar field, a float field, and we need to sample a vector field. That's what the gradient is. It's an XYZ coordinate, and so for that we're going to use a volume sample vector. And let's connect that. It's pretty much the same. It's just this samples vector, and the other one samples a float. So grad, and let's multiply that with our noise here. We can always normalize just to be sure, because it's basically a normal, and then we're going to add that, and boom, now we're talking. So let's change this, and let's increase the whirling. And this is basically volume displacement, as if we're working on a volume. And let's try and push this. Now the display, pardon me, the display is not very accurate because it's very low res volume. So let's increase this to 0.1. We should be able to see all the details of the whirly. It's too low. Let's take a look at the geometry of this actually. I'm curious because sometimes the SDF doesn't show, and then once you convert it you can see it. Cool, okay. So let's do this. Let's invert this value. Sorry. Let's invert this value. Let's see what we get. It's getting slower obviously because we're also converting it at the same time. Okay, well, there's a reason for it being slower. So you can see what kind of results we can get. Now the thing is, I'm gonna try and explain why we're getting this. It's definitely a very, very interesting thing. And let me lower the resolution just a tiny bit and set this to maybe 333. Okay, and let's compute again. Now let me explain why that is. Okay, now let me explain why that is. Now we have the surface. Okay, we have the gradient, which is the normal, and then what we use for the noise is the point position. So we have a point here that is a P1. When we run that from the noise, we're going to get a value of 0.5, let's say. Okay, that point, there is another one below it because the volume is filled with data. It's not empty. This point here is going to be run through the noise. It's going to get a value of 0.5. So if we have points that are stacked this way and points this way, and then we use all that data to run a noise, that let's say the noise will give us a value that pushes the data in this direction. This guy here will get a value higher than this, and the reason for that is because based on its depth, based on its where it is in space, and so we'll end up with something like this pushed in space. And if we keep doing this part here, for example, can get pushed all the way here. This part can get pushed all the way here. This part can get pushed all the way here, and that's why we're getting these floating pieces outside. Now we're displacing everything based on the normals, based on the gradient. So if I lower this value, you can see we're actually rockifying this, and this is the key. This is the secret to the stuff we're gonna be doing. The other stuff is just an intro. This is the key part. This is like the very interesting thing. Now, the other thing that we're gonna run into is we're gonna start seeing stuff in space, and we're gonna let's see where I can. So this part here, this guy, see how it's gonna build up. It's gonna overlap on top of the other detail, and it's gonna start, generating stuff on the fly, generating data out of nowhere. And this volume mixing part is just insane. We're gonna be creating a lot of cool stuff. Let me show you. Let's take this to the next level. Let's do an add here, and instead of using the point position as it is, I'm going to connect a noise to it. And now we're talking. Now we're taking anything and making rocks out of it. And this is the modifier I've made. It's basically a rockifier that takes any geometry and can do this to it. And so the other thing that we can do is we can start using all the breakups in the whirly. We can offset the noise, definitely not the intention. So let's change it to 3D noise. We can break this noise the same way we did with in the 2D texture thing, and that will allow us to create very interesting patterns. Now let me do something. So this is 3. Let's fit the range of this between so the min and max, it's going to be -1, -1, -1, and then let's say 2, 2, 2, and 7, 7, 7. And let's connect that to the frequency and see what we get. Now we're taking noise and using that to drive the frequency. It's probably too much. Let's try 3, 3. Sorry, I meant to lower it. So let's try 1, 1, 1, and 4, 4, 4. 1, 1, 1. So yeah, sometimes it doesn't cook, so I needed to change back and forth. And look at that. And actually, let's go back to the sphere, because it may not be very, yeah, this is the kind of stuff we're going to be creating. Now look at this detail here. And this, it's going to be pushing volume in and out and creating more interesting details. And remember, if we look at this as a surface, we can see it. And let me show you one more cool thing, and we're gonna stop this video. If we start moving this, we're going to do something like that. And all the way through, we can choose any level we want to create rocks. Okay? We can go as high. See this? This, for example. This stuff, this, what's happening there, there is no way you can get that using any other technique. Even in sculpting, there is no way you're going to be able to create that. And this is just insane in terms of what we can do with it. And with just how much nodes? Just this much nodes. Okay, now one more thing. Let's increase this to -1. I want that. And now we have a lot of interesting rocks that we can simply use with an RBD sim, make them fall onto the ground. Each one of them is unique, so we can easily scatter them nicely. Now let's see, can we do that? Let me try something. Let me try assembling this and do an exploded view. This is going to work, obviously. Okay, yeah, exploded view. We have all these pieces and then this block together. And what we can do is we can do a point VOP. We can do a grid. Let's see, we can do, yeah, let's do this. Let's do a point VOP and connect the point number to the position. See what we have. Now they're very separate. Let's multiply this by a constant, and I'll explain what I'm doing in a second. Yeah, so see, we're aligning everything. In each one, we're aligning it to a specific point. See, let's change this. Yeah, I mean, there is an easy way to do that, but I'm not going to worry. I was trying to align each one of them on a line, basically, so we have a straight line of debris or objects that we can use. But you guys get the idea. So now we're going to create one asset using this method, and hopefully, I think that's pretty much it for this week. So now we're going to continue and explore new noise that we can use to create interesting rocks. And the noise that we're going to be looking at is called the unified noise, which is the one that comes with the height field node. It's a little bit slow overall, but I think it's definitely worth waiting for it. The end result is very interesting. We can recreate something similar, but I would rather show you guys this node and use it. So I'm gonna copy what we have before, so these guys, and then instead of using these guys, the whirly, I'm going to delete that. And instead of using a negative value, I'm going to negate the normals. So I don't have to multiply my noise by -1. Now we can multiply that by 1. And I'm going to add a unified noise. And we're going to connect P, which is here. And let's add that. And now we should have something interesting. Cool. And I'm gonna change the noise to F2 minus F1. I'm gonna change the fractal. You can see already it's creating some interesting stuff. I'm gonna change the fractal to terrain. And I'm gonna set the noise to, you can see already it's creating some very, very interesting details. And I'm gonna copy this guy, paste relative. Actually, you know what? I need to, yeah, I have a shortcut. Yeah, so I need to use the shortcut, Alt Z. And I'm gonna set this value to 0.4 to add more rocks, to make it, sorry, let's try to, maybe we'll leave it 1.2. Cool. And then the final amplitude, I'm gonna copy this as well, and then paste relative reference, and I'm gonna change the amplitude so it's not that extreme. Let's try 0.4. I'm gonna tweak some options here. I'm gonna tick on fold. I didn't change much, but once we include these guys, it's gonna change. So I'm gonna turn off the auto update, and I want to change a few things. So first of all is the lattice warp. I have a previous values that I don't think they will work in this example, but I'm gonna try and put the same values and then go from there. So basically this adds a little bit of deformation. Cool. Yeah. So see how we have much more breakups now in the upper layer of the rocks. And let's not, yeah, I'm not gonna change the resolution yet. And there is a lot of interesting behavior, and once I increase the resolution, we'll see that. The last thing I want to add is a noise. I want to change the point position itself. So I'm gonna turn off the auto update feature, and I'm gonna change this. So let's expose these guys and tweak them at the upper level. And what else do we need? Let's expose the frequency as well, and call this unified frequency unified, so we know which one it belongs to. And then there is tons of options here. I'm not gonna go over each one of them. Hopefully you guys will be able to spend some time and play with those attributes. Now let's turn on the auto update back again. And this is the more advanced rockifier that I've created. Right now it's doing stripes because the noise that I have is because the noise that I added to the point is float. But I like this, so I'm gonna lower the resolution and show you guys just what you can get. You know, you can run into a lot of happy accidents, which happened to me as well while working on this project, and you will discover a lot of new things. This field by itself is still unexplored, and we're just scratching the surface as to what we can do with it. So let's take a look at this. That's the ISO surface too high, so let's go back in. Cool. So we get some really cool details here. And let's fix the noise. It's actually 3D noise. Interesting. Then we must have missed one value. Okay, let's check that. Yeah, I think the frequency unified is broken, that's why. So it was just multiplying, and the unified noise has a multiplier per axis. So I'm gonna copy this again and paste the relative reference. And this is really cool. Okay, let's lower the amplitude of the noise. The position noise, I don't want to affect the position too much. And again, we're waiting for the surface, so I shouldn't be doing that. Should be looking at this, and I think we're in a good shape now. Yep. So look at the result, and if you think by just adding one noise we can get this, imagine if we layer a lot of things on top of each other, what kind of results we can get. Now let me take it further, and I'm going to add the cellular noise, and let me go up and reduce this to 4, and let's dive back in. Actually, let's view this instead, and I'm going to disable this, and I'm going to use the UV coordinate to be this guy. I'm going to use the border, see what we get. Cool. Okay, so let's I think we can disturb the position a little bit more. So what I'm going to do is I'm going to add a multiply by a constant here and use a different noise for just use a higher amplitude for the noise for the cell to break the edges. So instead of 1, I'm going to set it to 4. Yeah, and that should break them up. And now right now it's pushing everything out, but I don't want that. I want to invert that. I want to create cracks basically. So I'm going to fit range this guy. Sorry. I'm going to fit range this and basically invert it between minus this way. Let's connect that. Okay, cool. So now we have that, but it's too much. I think it's a little bit too extreme. So let's set this to 0.1, something like that, and let's see how it is added to with everything else. Actually, we shouldn't multiply. Yeah, let's multiply. That's fine. I'm gonna copy this. I'm gonna copy this, and let's connect this guy. Add this. And I'm gonna set this back to 1. And what I'm going to do is lower this guy, so 0.1, and use this as a controller. Let's multiply that, and let's turn on back the noise. Let's see what we get. Yeah, I'm not liking how this is going, what the cracks are doing. So let's try inverting that and see what we get. Okay, cool. Yeah, I think this works better. Let's try 0.2. It's definitely pushing everything out, so it may not be as useful, but just an idea to show you guys what we can do. And let's go a bit more high res, so 0.1, and let's take a look just at the volume itself. Okay, cool. And let's take a look at this now. Awesome. So now we have big cracks between the parts. And the cool thing is it's not just, it's not uniform. There's a lot of interesting interleaving of details between the various parts. Now let's take, what can we take? Let's take a box, and let's try to make the size similar to this. Okay, and let's transform it so it's 2 units, 2 times bigger, sorry, something like that. Let's do we need more space. Let's go PDB from polygon. And it's a surface. It's a density. It just needs this to scatter some points. So that's good. Scatter some points. Okay, let's Voronoi fracture this. Okay, cool. Let's transform it. So 0.3 action, create reference, create another reference, and let's do the inverse. Okay, and let's delete. I just want to quickly delete some parts. So there, I'm gonna assemble this. Pardon me. And bounding box, set it to points, and let's add a bit more details. And it's not at the top. Okay, something like that. Okay, and let's see what we get. I'm gonna convert this into volume, see how dense it is. Okay, cool. And let's just run it through this noise. I'm not gonna change anything. Obviously the scale is going to be off, but you guys get the idea. So I think in the next video I'm going to show one more example, one more advanced example that uses the unified noise, and I think that would be it for this week. Now look at that. One modifier, one node, and we are able to create this all on the fly. And we haven't started doing any crazy processing yet, because remember all the stuff we did with the texture, where we import, where we can offset the Worley pattern, where we can offset, change the point and disturb anything we want. We can add a lot of complex stuff, and look at this. It just works. And let me show you one more thing. So because it's an SDF, it does some very interesting things when we start going in, because it's going to sample a different volume, so we see different details being revealed in the mesh. And man, I really like the parts where it's super flat and the parts where there's a lot of details. That mixing is very, very interesting. And then these cracks are they're not very disturbed, so I want to change that a tiny bit. Yeah, here, this is our cracks, and you can see them towards the end. They're affecting too much. I'm not liking the way the cracks are working, but I think it's fine for now. I'm not gonna worry too much about it. And let me change this to 0.1. Okay, cool. Let's do one last thing. How much resolution do we have? Let's increase this to 0.6. And then I promise I'm gonna stop the video. I just want you guys to see the result of this being cooking live. And so we have 0.06 now subdivision, which should give us tons of voxels. And the cool thing about this is the details is not going to change between the low res and the high res. So you can work on the low res Obviously, you're not going to be able to see it as clearly as you can with the high res, but everything will be the same. You just, when you go higher res, you're going to get more details. And it's very important to have this kind of workflow. It's not like when you do a sim, for example, you do a sim at low resolution, you get something, and then you go high res, it's completely different. With this, it's always the same, it's just more resolution. So you can see all the computation is inside this node, and actually what's the slowest part of that is the unified noise. But again, I wouldn't call it slow, because how much data we have? Let's set this to 0 first. How much data we have? We have 6 million points, so I wouldn't call it slow. And we have how much? Yeah, it's 74 million voxels. And look at the result. Now, obviously, there is gaps that we're starting seeing, and by just adding a little bit of banding, extra voxels. If I look here and click W, you can see we can add a little bit of room, and that will fix all the issues. In this video, I'm gonna go over the setup of how I created this. For the sake of time, I'm not gonna recreate everything from scratch. I think you guys all know exactly the steps that I went through to create this, but I'm gonna go over the graph and show you what I've done. And it's actually really, really simple. Now, obviously, there's a crucial part before you pass the data into a volume. There's a crucial part before you pass the data into volume. It has to be perfectly suited to create something interesting. You cannot just pass anything and you expect it to work. Now, there's a lot of R&D that you guys will have to research as well to achieve your specific goal, to achieve specific type of rocks or things like that. And I would say 60% of this is based on the input geometry. And if you don't have an interesting geometry that has basically the majority of the details, then you're not going to be able to get anywhere with just using volumes. You may be able to make anything look like rocks, but you won't be able to build any interesting structure. So the main thing with this guy is, I think we all know the volume processing method by now, and the main thing for this guy is this. So the way I've done it is I created a line which has couple of points. There's so many ways to do the same thing, and I didn't rethink many times on how I can do it faster, or I just did it. This is the first thing that came to my mind. So I took a line and then I added a point vault to shift the points up and down along the y-axis, so I get randomization. And then I deleted everything and sorted the points by height, and then I connected them again and I extruded that, so I have this. Okay, and then I separated each face basically separated each face so it's unique. Let's set this for a flat wireframe. Yeah, and then I looped over each one of them and broke it down into pieces. So I took the first part here, added a Voronoi, extruded it, created a volume out of that, added some points, and then did a Voronoi fracture. Okay, and then this is the final result. I also added an expression to name each one of them so they don't overlap. Don't worry about this. We're gonna go over this once you guys feel comfortable about all the stuff I demoed this week. And then once I finished that, once we have the fracturing going, actually let's put down a color node and colorize everything based on name, I believe. So we need to promote that. Let's set it to primitive. Cool. So that's the pieces. And then we also, I believe they don't have depth. Yeah, some of them have two pieces in front of each other, and so I'm gonna utilize that and remove chunks out of that volume. So the next thing, I loop over each piece and transform it randomly, transform it a little bit, and then I don't remember. Yeah, and then I added a grid that I copy randomly into a single point, which is basically the centroid, and then I copy this grid and use that to do a Boolean. So I cut each piece randomly. Each piece it gets a clipping plane that removes part of it, and then I group those edges and fill them back in, and I repeat that to all of them. And this is what I have. I have a very interesting wall. This kind of details, for example, is crucial to the layering. I'm in control of that now. It's not just up to the volume to give me what they want, what it will produce. I can control where the details are happening and things like that. This as well is very, very interesting. There's a lot of interesting details inside the base geometry, which is actually very, very simple, just polygons at the moment. And then I subdivided that and added a little bit of noise to break the edges. So just I'm not changing this vector, just these faces, so up and down. And then did a VDB from polygon for all of that. Don't worry about this yet. And then VDB analyze to compute the gradient of this. And then once we run an operation on the volume, it's much better to do one change at a time using that normal. We don't want to change the data too much, because we may start seeing issues. Actually, we're not going to see issues, but it's not going to be very accurate. Now I do one change to take it from this level to this, and then I compute the gradient again, because I want to add another level on top of this. So this is not the final result. I compute the gradient again to be updated based on these details, and then add another. Let's see, which one is it? So this is very, very similar to what we've done. It's actually just a unified noise. That's it. And then this guy is basically a very simple noise. Again, don't worry about this. We're gonna get there. And this is the final result. Just a little bit of detail. Well, maybe not just a little. Too much details with this modifier, and then a tiny distortion across the board. And this is the final result. So this is the example. But again, it's all because of that original geometry that I created. And this stuff, the volume stuff, is very, very simple. And let me show you the high-res version. Okay, so I loaded the mesh, and this is the final high-res version. I think it's exactly the same setup. I just increased the resolution of the volume, and that's it. Let me show you the back. Also has a lot of interesting details. And see, these cracks are not coming from the volume. They're all originating from the mesh, from the original mesh. And that's a crucial part. But again, adding all these cool details is crucial. Now, I will release this setup as we get close to the assignment. I want to make sure that you guys all build this from scratch, and then hopefully by the end of the week I'll release everything that you guys need to use. I'm gonna explain how to go and work on this week, and the main thing that I'm interested in seeing is you guys understanding how to create an interesting geometry at the beginning, whether it's using Voronoi, whether it's a custom made geo. I don't really care about the technique. I showed the Voronoi because it can lead to creating some interesting rock-like structure, but you can use any method you want. Like, for example, this one, we use Voronoi, but you can use any method you want. And then I would like to see something similar to this. If you have another idea on how to achieve this, that's totally fine. But what I would like to see is these type of cracks in the mesh, and a lot of variation, basically small, mid, and high details. And then once you guys are done with that, you can work on, you can create anything using the new method that I showed. So the new method that has that uses SDF. I want to see two things. One created with no SDF, with just volume and volume processing, and another one with an SDF, with using the SDF workflow and using the gradient to displace the mesh. And then feel free to create anything you want. There is no restriction on the art direction or anything. I just want to see a good use of the techniques I showed and a very interesting input geometry, because I'm very confident once you understand how the volume works, it's really easy to make good use of it and add interesting details. And I would like also to see the technique of the edge displacement implemented, the one where we displace the original Voronoi. You can apply that method to anything you want. It doesn't have to be a Voronoid mesh. It could be anything you have. But if it's a simple geometry and it doesn't have breakups, I would like to see that technique implemented. And I think that's pretty much it. Thank you, guys. And one last thing. The stuff I've been doing is a variety of R&D and final assets. I want you guys to do R&D. You can do it all in the same theme file, and then once you have the R&D, I want you guys to go through and create individual assets, individual project using the scripts, maybe 4 or 5 or 10 assets, depends on how much time you have for this, and create them and generate all the data needed, the low-res mesh, the high-res mesh, and the S file for Arnold. And I think that's pretty much it. Thank you guys for all the hard work.